You are listening to Redis for Developers, mastering in-memory data storage for modern applications. Like and subscribe to keep up to date on our latest audiobooks. Redis for Developers, mastering in-memory data storage for modern applications. The heart of modern applications. Introduction to Redis. Imagine trying to navigate a bustling city with only a paper map and a compass. You'd eventually get where you need to go, but it would be slow, inefficient, and prone to error. Now imagine having a real-time GPS with live traffic updates, knowing exactly where you are, where you're going, and the fastest way to get there. This is analogous to the shift we've seen in application development. Modern applications demand speed, responsiveness, and the ability to process vast amounts of data in the blink of an eye. We're no longer building static websites. We're crafting dynamic experiences, real-time dashboards, and interactive platforms that serve millions of users simultaneously. The modern application landscape and data challenges. Today's applications operate in a landscape defined by several key demands. Real-time functionality. Users expect instant feedback, from live chat messages appearing immediately to financial trading platforms reflecting price changes in milliseconds. High concurrency. Millions of users might interact with an application at once, requiring systems that can handle a massive number of simultaneous operations without degradation. Scalability. Applications must grow seamlessly to accommodate increasing user loads and data volumes, often needing to scale both horizontally, adding more machines, and vertically, making machines more powerful. Traditional relational databases, while excellent for ensuring data integrity and complex querying, often struggle with these demands when operating at extreme scales or with specific types of workloads. They can become bottlenecks for operations that require very low latency, such as caching frequently accessed data, managing ephemeral session information, or processing a high volume of simple, rapid writes and reads. Imagine an e-commerce site experiencing a flash sale. If every product view or cart addition resulted in a complex, high-latency database query, the system would quickly falter, leading to frustrated customers and lost revenue. This is where specialized data stores like Redis step in to fill the gap. What is Redis? A high-level overview. At its core, Redis stands for Remote Dictionary Server. But don't let the simplicity of its name mislead you. It's a powerful, versatile, and incredibly fast open-source in-memory data store that has become an indispensable tool for developers building modern, high-performance applications. Let's break down its core characteristics. In-memory data store. This is Redis's primary strength. Unlike traditional databases that primarily store data on disk, Redis keeps a significant portion of its data in the computer's volatile main memory, RAM. Accessing data from RAM is exponentially faster than fetching it from a hard drive or even a solid-state drive, SSD, resulting in microsecond-level response times. Open source, BSD licensed. This means Redis is free to use, modify, and distribute, fostering a vibrant community and continuous innovation. Blazingly fast. Redis is often cited as one of the fastest databases available. Its single-threaded architecture, coupled with its in-memory nature and highly optimized C code, allows it to achieve hundreds of thousands, sometimes millions, of operations per second on a single instance. Versatile, powerful data structures. This is where Redis truly distinguishes itself from simple key-value stores. While you can store basic key-value pairs, Redis natively supports a rich set of data structures: strings, hashes, lists, sets, and sorted sets. This built-in support for complex data types means developers don't have to serialize and deserialize data themselves. Redis handles it efficiently, offering powerful commands to manipulate these structures on the server side. More recently, advanced data types like streams, hyperlog, and geospatial indexes have further expanded its capabilities. Support for various programming languages. Redis is not tied to any single programming language. Thanks to its simple, text-based protocol, client libraries exist for virtually every popular language, including Python, Node.js, Java, C, Go, Ruby, PHP, and many more. This allows developers to integrate Redis seamlessly into their existing technology stacks. Redis was created by Salvatore Sanfilippo, an Italian developer, and was first released in 2009. Initially built as a temporary solution to improve the scalability of a project, it quickly garnered attention for its unique approach to data storage and handling, evolving into one of the most widely used NoSQL databases. Why developers choose Redis? Core advantages and principles. The reasons for Redis's widespread adoption by developers stem directly from its core advantages. Speed and performance. As mentioned, the in-memory nature is paramount. Every operation is designed for maximum efficiency, making Redis ideal for latency-sensitive applications where sub-millisecond response times are critical. Rich data model. Redis isn't just a basic dictionary. It's a toolkit of sophisticated data structures. Need a counter? Use an atomic increment on a string. Need a leaderboard? Use a sorted set to track scores. Need a chat room or activity feed? Streams are perfect. This flexibility reduces the need for complex application-level logic to manage data relationships, allowing Redis to do the heavy lifting closer to the data. Atomic operations. Redis guarantees that all operations on a single key are atomic. This means that a command either completes entirely or doesn't execute at all, even in a concurrent environment. If multiple clients try to increment a counter simultaneously, Redis ensures that the final count is correct, without race conditions or partial updates. This simplicity makes it easier to write robust, multi-threaded applications. Simplicity and ease of use. Redis is known for its elegant design and straightforward command set. Getting started is easy, and its command line interface, CLI, is intuitive for exploration and debugging. The widespread availability of mature client libraries further simplifies integration into any application. Versatile use cases. While often associated with caching, Redis is far more than just a cache. Its general-purpose nature allows it to serve in various roles, from session stores to real-time analytics engines, which we'll explore shortly. Persistence options. Despite being an in-memory store, Redis offers robust persistence mechanisms, save-to-disk options, that allow you to save your data to disk, ensuring that even if the Redis server restarts, your data is not lost. This makes it suitable for scenarios where data durability is important. High availability and scalability. Redis provides built-in features for high availability, ensuring continuous operation even if a server fails, and horizontal scalability, distributing data across multiple Redis instances to handle larger datasets and more traffic. Tools like Redis Replication, Redis Sentinel, and Redis Cluster allow developers to build incredibly resilient and scalable systems capable of surviving node failures and handling massive loads. Common Redis use cases in modern development. Given its speed, flexibility, and robust feature set, Redis shows up in a surprising number of places within modern application architectures. Caching. This is perhaps Redis's most well-known role. By storing frequently accessed data, like product details, user profiles, or query results in Redis, applications can avoid repeatedly querying slower primary databases, significantly reducing load and improving response times. Session management. Web applications often store user session data, login status, shopping cart contents, personalized settings. Redis provides an extremely fast and reliable store for this ephemeral data, especially for stateless microservices architectures that need a centralized, fast session store. Real-time analytics and leaderboards. The atomic increment operations and sorted sets make Redis perfect for tracking likes, views, scoreboards, and other real-time metrics. Imagine a game's leaderboard updating every second. Redis can handle the rapid updates and retrievals with ease. Message queues and PubSub. Redis lists can act as simple, fast message queues for asynchronous task processing. Its publish-subscribe mechanism allows for real-time messaging, enabling features like chat applications, live notifications, and event-driven architectures, where services can communicate without direct coupling. Distributed locks. In distributed systems, it's often necessary to ensure that only one process or server can perform a specific operation at a time. Redis can be used to implement distributed locks, providing a simple yet effective way to coordinate actions across multiple application instances. Rate limiting. To prevent abuse or ensure fair usage of APIs, applications often implement rate limits. Redis's fast counters and expiration capabilities are ideal for tracking API calls per user or IP address within a given time window. Geospatial applications. Redis has native commands for storing and querying geographical coordinates, making it invaluable for location-based services, finding points of interest within a certain radius, or calculating distances between locations. Full-text search via modules. While not a native search engine, Redis can be extended with modules like Redis Search to offer powerful full-text search capabilities, complex query filtering, and auto-completion, turning a simple data store into a versatile search index. These are just a few examples. The versatility of Redis often leads to creative solutions for various architectural challenges. Structure of this book: Your Journey to Redis Mastery. This book is designed to take you on a progressive journey from understanding Redis's basics to mastering its advanced features and applying them in real-world scenarios. We'll cover Part 1, Fundamentals. We'll begin by getting you set up with Redis, understanding its core command line interface, and then dive deep into its fundamental data structures: strings, hashes, lists, sets, and sorted sets. You'll learn the core commands and typical use cases for each. Part 2, Advanced Features. Building on the fundamentals, we'll explore powerful capabilities like atomic transactions, performance-boosting pipelining, real-time publish-subscribe messaging, and extending Redis's functionality with Lua Scripting. We'll also dedicate a chapter to Redis Streams, a cutting-edge data structure for event sourcing and durable queues. Specialized data types like hyperloglog for unique counts and geospatial functions will also be explored. Part 3, Practical Applications. This section focuses on applying your Redis knowledge to solve common developer problems. We'll examine in detail how to use Redis for various caching strategies, user session management, implementing robust distributed locks, building effective message queues, and creating advanced rate limiters. We'll also introduce the exciting world of Redis modules, which extend Redis's capabilities into areas like search, JSON document storage, and graph databases. Part 4, Operations and Best Practices. Finally, we'll delve into the operational aspects of running Redis in production. This includes understanding its persistence options for data durability, ensuring high availability with replication and Sentinel, scaling your deployments with Redis cluster, and best practices for monitoring, performance optimization, and securing your Redis instances. Our goal is not just to teach you commands, but to instill a deep appreciation for why Redis operates the way it does, and how to leverage its strengths to build resilient, high-performance applications. Getting ready for the journey. To get the most out of this book, a basic understanding of programming concepts and general application architecture will be beneficial. You don't need prior Redis experience, nor do you need to be an expert in distributed systems. Everything you need will be explained clearly and concisely. The best way to learn Redis is by doing. Throughout this book, I encourage you to actively experiment. We'll primarily use the Redis CLI, the Redis command line interface, to interact directly with the server. This hands-on approach will solidify your understanding. While we won't be writing extensive code blocks in specific programming languages due to the nature of this book's format, we will often outline conceptual pseudocode or describe how a developer would integrate Redis into their application using various client libraries. In the next chapter, we'll roll up our sleeves and get Redis installed and configured, preparing your development environment for the exciting journey ahead. Let's begin. Getting your hands dirty. Installation, CLI, and first steps. Before we can unlock the full potential of Redis, we need to get it up and running on your machine. This chapter will guide you through the process of installing Redis, familiarizing you with the essential command line tools, and performing your very first interactions with the server. By the end of this chapter, you'll have a working Redis instance and the confidence to explore its core functionalities. Redis installation options. Redis is remarkably easy to install across various operating systems. We'll focus on common local installation methods, briefly touch upon using Docker for quick setups, and mention commercial cloud services for production-grade deployments. A. Local installation. The most direct way to get Redis is to install it natively on your operating system. 1. Linux. For most Linux distributions, Redis is available through their package managers. This is often the simplest method. Debian/Ubuntu. To install, simply open your terminal and run sudo apt update. Sudo apt install Redis server. Redis will usually start automatically as a service after installation. Red Hat CentOS Fedora. You might need to enable the EPEL extra packages for Enterprise Linux repository first. Sudo DNF install EPEL release for Fedora RHEL 8+, or sudo yum install EPEL release for CentOS RHEL 7. Then install Redis. Sudo DNF install Redis or sudo yum install Redis. Start the service. Sudo systemctl start Redis. Enable it to start on boot. Sudo systemctl enable Redis. Compiling from source, advanced specific needs. While package managers are recommended for most, you can always compile Redis from its source code. This gives you the latest version or specific control over the build. You'll need GCC and make. Download the latest stable version from redis.io/download, extract it, then make. After compiling, you can run sudo make install to place the binaries in your system's path. 2. macOS. Homebrew is the easiest and most recommended way to install Redis on macOS. If you don't have Homebrew, you can find installation instructions on brew.sh. Open your terminal and run brew install Redis. After installation, Homebrew will tell you how to start Redis, typically using brew services start Redis. Or you can manually start it from the terminal. Redis server. 3. Windows. Officially, Redis does not provide native Windows binaries due to historical reasons and strategic focus on Linux environments. However, there are excellent ways to run Redis on Windows. Windows Subsystem for Linux, WSL. This is the most recommended method for Windows users as it provides a full Linux environment directly within Windows, allowing you to follow the Linux installation instructions above. Install WSL, then install your preferred Linux distribution, e.g., Ubuntu from the Microsoft Store, and proceed with the apt install Redis server command within your WSL terminal. Docker Desktop. Docker provides a containerized way to run Redis, which is isolated from your Windows system. This is an excellent option for development. See Docker section below. Unofficial native builds. Historically, Microsoft maintained a Windows port of Redis. While this is now deprecated and not recommended for production, you might find old binaries available for local development use. However, WSL or Docker are far superior and more up-to-date options. Docker. Quick setup for development environments. Docker offers an isolated, portable, and quick way to get Redis running without cluttering your system. If you have Docker Desktop installed, you can start a Redis instance with a single command. Docker run name myredis, p6379, 6379 d Redis. Docker run, command to run a Docker container. Name myredis, assigns a human-readable name to your container. p6379, 6379, maps port 6379 on your host machine to port 6379 inside the container, Redis's default port. D runs the container in detached mode in the background. Redis specifies the official Redis Docker image. To stop the container, Docker stop myredis. To remove it, Docker rm myredis. C. Cloud Managed Services, brief mention. For production applications, especially those requiring high availability, scalability, or minimal operational overhead, cloud-managed Redis services are often preferred. These services abstract away the complexities of managing Redis infrastructure. Examples include Redis Cloud, a fully managed service by Redis Labs, the company behind Redis. Oz Elasticache for Redis, Amazon's managed Redis service. Azure Cache for Redis, Microsoft Azure's managed Redis service. Google Cloud Memoristore for Redis, Google Cloud's managed Redis service. While we won't cover these in detail, be aware that their connection methods often involve unique hostnames, port numbers, and sometimes authentication tokens provided by the cloud provider. Starting and stopping the Redis server. Once installed, interacting with Redis usually involves two main executables: Redis server, the server itself, and Redis CLI, the command line interface client. 1. Starting Redis server. If you installed Redis via a package manager or homebrew, it often starts automatically as a system service. You can check its status with commands like sudo systemctl status Redis, Linux, or brew services list, macOS. To start Redis manually from your terminal, simply type Redis server. By default, this will run Redis in the foreground, meaning your terminal will be occupied, displaying Redis logs. To run it in the background, as a daemon, you can provide a configuration file, covered next, or explicitly set the daemonize option. For now, running it in the foreground for learning is fine, or simply start it via your system's service manager. 2. Stopping Redis server. The safest way to stop a running Redis instance is by using the Redis CLI tool to send a shutdown command. This allows Redis to perform a clean shutdown, saving any pending data to disk if persistence is enabled. In a separate terminal window, run Redis CLI shutdown. If Redis is running in the foreground, you can also usually stop it by pressing Ctrl+C in the terminal where it's running. This might not always guarantee a clean shutdown, especially if it's under heavy load. Avoid using kill-9 as it will not allow Redis to save its data cleanly. Interacting with Redis. The Redis CLI. The Redis CLI is your primary tool for communicating directly with a running Redis server. It's an interactive client that allows you to send commands and view responses. 1. Basic connection. If Redis is running on the default host, 127.0.0.1, which is localhost, and default port 6379, you can simply open a new terminal and type Redis CLI. You should see a prompt like 127.0.0.1:6379 indicating you are connected. 2. Connecting to specific instances. If your Redis server is on a different host, port, or requires a password, you can specify these options. H hostname. Specify the host, e.g., Redis CLI H192.168.1.100. P port. Specify the port, e.g., Redis CLI P6380. A password. Provide an authentication password, e.g., Redis CLI A MySecret password. 3. Essential Redis CLI commands. Ping. A simple command to check if the server is alive and responding. It should return pong. 127.0.0.1:6379 ping. Pong. Echo message returns the provided message. Useful for testing connectivity or echoing strings. 127.0.0.1:6379 echo. Hello Redis. Hello Redis. Select DB number. Redis supports multiple logical databases, numbered from 0 to 15, by default. These are entirely separate namespaces. Keys in one database do not conflict with keys in another. Most applications use database 0, but select allows you to switch. 127.0.0.1:6379, select 1. OK. 127.0.0.1:6379 Notice the prompt changes to 1, indicating you are now in database 1. 4. Key management and inspection. Redis organizes all its data as key value pairs. These commands help you manage and inspect your keys. Set Mikey hello will cover set in detail in Chapter 3. EXISDS key. Checks if a key exists. Returns 1 if it does, 0 otherwise. 127.0.0.1:6379 EXISDS Mikey. Integer 1. 127.0.0.1:6379 EXISDS non-existent key. Integer 0. Type key. Returns the data type of the value stored at key, e.g., string, hash list, set, zet, stream, none. 127.0.0.1:6379 type Mikey. String. TTL key. Returns the time to live TTL of a key in seconds. If the key has no expiration, it returns. If the key does not exist, it returns -2. Del key 1 key 2 deletes one or more keys. Returns the number of keys deleted. 127.0.0.1:6379 del Mikey. Integer 1. Keys pattern returns all keys matching a given pattern. Warning. Never use keys in a production environment or on a busy server without extreme caution. It's a blocking command that iterates over all keys in the database, which can freeze your Redis server for a significant amount of time if you have many keys. It is only suitable for development or debugging on small datasets. For production, use scan queries, which are out of scope for this introductory chapter. 127.0.0.1:6379 Set user. 1. Name Alice. OK. 127.0.0.1:6379 Set user. 2. Name Bob. OK. 127.0.0.1:6379 Keys user. 1. User 2 name. 2. User 1 name. RANDOMKY returns a random key from the database. Not particularly useful for application logic, more for exploration. 5. Monitoring monitor. This command streams every command processed by the Redis server in real time. It's incredibly useful for debugging and understanding what's happening on your server, but it can generate a lot of output quickly. 127.0.0.1:6379 Monitor. OK. 1,678,880,6,400.1234560 127.0.0.1:54321. Set. Test key. Testful you. 1,678,880,6,400.65432 1:127.0.0.1:54322. Get. Test key. You'll need a separate Redis CLI window to run other commands while monitor is active. Info provides a wealth of information and statistics about the Redis server, including memory usage, client connections, replication status, persistence settings, and more. It returns a categorized list of key value pairs. 127.0.0.1:6379 Info. Hash server. Redis version 7.0.8. Redis Jitcha 1 0000000. Redis builded 3A5047B 38-7C943. Redis mode standalone. OS Linux 6.2.0 to 20 generic x8664. Hash clients. Connected clients 1. Understanding Redis configuration. Redis.conf. Redis uses a configuration file named redis.conf to control its behavior. This file dictates everything from network settings to persistence strategies and security options. 1. Locating the configuration file. The location of redis.conf varies based on your installation method. Package managers, Linux. Often in etc/redis/redis.conf or etc/redis.conf. Homebrew, macOS, typically in /usr/local/etc/redis.conf. Source compilations. A redis.conf example often resides in the root directory of the source code. You'll need to copy and edit it. Docker. When running Redis in Docker, the container uses a default redis.conf internally. For custom configurations, you would typically mount your own redis.conf file into the container or pass configuration directives directly via Docker run arguments. 2. Key configuration directives, important for developers. Let's look at some critical settings you might encounter or modify. Bind 127.0.0.1. This specifies the IP address Redis will listen on. By default, it's 127.0.0.1 localhost, meaning it only accepts connections from the same machine. To allow connections from other machines, e.g., for a development server accessible by your team or by a front-end from a different container, you might change this to 0.0.0.0 all interfaces. But be aware of security implications if also publicly exposed. Protected mode yes. This is a security feature. If set to yes, default, Redis will only accept connections from localhost unless you explicitly configure a bind IP, a require password, or use TLS. Keep it yes unless you know what you're doing. Port 6379, the TCP port Redis listens on. 6379 is the standard. Demonize no, If set to yes, Redis runs as a background process, a daemon. No means it runs in the foreground. Loggable notice controls the verbosity of Redis logs. Options include debug, verbose, notice, warning. Notice is generally a good default for production. Databases 16 defines the number of logical databases Redis supports. Default is 16, numbered 0 to 15. Require password. Highly recommended for production, this sets a password that clients must provide to connect to Redis. If set, clients must authenticate using the auth password command or A option with Redis CLI after connecting. Always set a strong password in production. Max memory bytes and max memory policy. Extremely important for managing Redis's memory usage. Max memory sets a hard limit on the amount of memory Redis can consume. When this limit is reached, max memory policy dictates what happens, e.g., evict least recently used keys, random keys, or block writes. These prevent Redis from consuming all available RAM on your server. 3 dynamic configuration changes: CONFIG and CONFIG set. Some configuration directives can be changed dynamically without restarting the server using the CONFIG set command. CONFIG get parameter retrieves the current value of a configuration parameter. 127.0.0.1:6379 CONFIG get loggable. 1. Loggable. 2. Notice. CONFIG set parameter value. Sets a configuration parameter to a new value. 127.0.0.1:6379 CONFIG set loggable debug. OK. 127.0.0.1:6379 CONFIG get loggable. 1. Loggable. 2. Debug. Note: changes made with CONFIG set are not permanent. They will be lost if Redis restarts unless you save the configuration using CONFIG rewrite. However, directly editing redis.conf and restarting Redis is usually the preferred method for permanent changes. Your first Redis commands, a quick tour of data types. Redis is known for its rich set of data structures. Before diving deep into each in dedicated chapters, let's execute a few common commands to get a feel for how they work. 1. Strings, the simplest value type. A key maps to a single string value. Set key value sets a string value. Get key retrieves a string value. 127.0.0.1:6379 set my first key. Hello Redis developer. OK. 127.0.0.1:6379 get my first key. Hello Redis developer. 2. Hashes, similar to a hash map or dictionary in programming languages. Keys map to objects, and each object has field value pairs. HSET key field 1 value 1 field 2 value 2 sets fields in a hash. HGTALL key gets all field value pairs from a hash. 127.0.0.1:6379 HSET user. Profile. 123 name Alice. Email alice@example.com age 30. Integer 3. 127.0.0.1:6379 HGTLL user. Profile. 123. 1. Name. 2. Alice. 3. Email. 4. alice@example.com. 5. Age. 6. 30. 3. Lists an ordered collection of strings. You can push pop elements from either the left head or right tail end. LPUSH key value 1 value 2 pushes elements to the left head of the list. LRANGE key start stop gets a range of elements from the list. 0-1 means all elements. 127.0.0.1:6379 LPUSH Midas list task C. Task B, task A. Integer 3. 127.0.0.1:6379 LRANGE Midas list 0. 1. Task A. 2. Task B. 3. Task C. 4. Sets an unordered collection of unique strings. No duplicates are allowed. SADD key member 1 member 2 adds members to a set. SMEMBRS key gets all members of a set. 127.0.0.1:6379 SADD tags Article 456, Tech, Programming, Redis, Tech. Integer 3, 172.0.0.1:6379, SMEMBRS tags. Article 456. 1. Tech. 2. Redis. 3. Programming. Notice tech was added only once. 5. Sorted sets. Similar to sets, but each member is associated with a score, allowing elements to be ordered. ZADD key score 1 member 1 score 2 member 2 adds members with scores to a sorted set. ZRANG key start stop with scores gets a range of members from the sorted set, optionally with their scores. 127.0.0.1:6379 ZADD leaderboard 100 player A, 150 player B, 75 player C. Integer 3, 127.0.0.1:6379 ZRANG leaderboard -1 WITHSURES. 1 player C, 2 75, 3 player A, 4 100, 5 player B, 6 150. The members are returned in ascending order of their scores. Introduction to Redis client libraries, conceptual. While Redis CLI is excellent for learning and debugging, real-world applications don't typically interact with Redis by shell scripting Redis CLI commands. Instead, they use client libraries specific to their chosen programming language. A Redis client library is essentially a wrapper around Redis's underlying communication protocol. When your application code calls a method like Redis client set, myvalue, the client library, establishes a TCP connection to the Redis server, usually on port 6379, translates your method call into the Redis protocol command, e.g. 3\r\n$3 $r\nset $r\n$5 $r\n$mikey $r\n$7 $r\n$myvalue $r\n. Sends this command over the network, receives the server's response, parses the response back into a format your programming language understands, e.g., OK or a string value. Every popular language has one or more mature Redis client libraries: Python, Redis Py; Node.js, Iordes Node-Redis; Java, Jedi's Lettuce; Go, GoRedis; C#, Stack Exchange Redis; Ruby, Redis RB; PHP, PHPredis Predis. These libraries handle connection management, command serialization, response parsing, and often provide convenient high-level abstractions, making it seamless to integrate Redis into your application logic. We will mostly be using Redis CLI for examples in this book for clarity and universality. But remember that the concepts translate directly to using these libraries in your development workflow. You now have Redis installed, know how to start and stop it, and can interact with it using the Redis CLI, executing basic commands across different data types. You're ready to dive deeper into each of these powerful data structures, starting with the fundamental building block, strings. The foundation, strings, simple yet powerful data. In the world of Redis, everything starts with a key. And for many of those keys, the simplest and most fundamental value you can associate is a string. Don't let the name, string, lull you into thinking it's only for text. Redis strings are incredibly versatile, capable of storing a wide range of binary-safe data. They are the backbone of many basic Redis applications, from simple caching to complex atomic operations. Introduction to Redis strings. A Redis string is the most basic data type you'll encounter. It's essentially a sequence of bytes. This binary-safe nature means you can store anything from a regular text string, hello world, to an integer, 123, a floating point number, 3.14, a JPEG image, or even a serialized object. Redis doesn't care about the content. It treats it as raw bytes. The maximum size for a Redis string value is 512 megabytes, MB. While you generally won't store entire files in Redis due to memory constraints, this generous limit allows for storing moderately sized objects or binary data. At its core, Redis strings are used as a basic key-value store, much like a dictionary or hash map where each key uniquely identifies a specific string value. This makes them ideal for straightforward lookups and storage. Basic string commands. Let's dive into the fundamental commands for manipulating Redis strings. Set key value. This command sets the value of key. If key already holds a value, it is overwritten regardless of its type. 127.0.0.1:6379. Set myname Alice. OK. 127.0.0.1:6379. Get myname Alice. 127.0.0.1:6379. Set myname Bob. OK. 127.0.0.1:6379. Get myname Bob. Get key retrieves the value of key. If the key does not exist, it returns nil. If the key exists but holds a non-string value, an error is returned. 127.0.0.1:6379. Get myname Bob. 127.0.0.1:6379. GET non-existent key. Nil. Setnx key value, set if not exists. This command sets the value of key only if key does not already exist. If the key exists, no operation is performed. It returns 1 if the value was set and 0 otherwise. This is useful for implementing simple locks or ensuring data is written only once. 127.0.0.1:6379. Setnx user, sign up, lock, locked. Integer 1. 127.0.0.1:6379. Setnx user, sign up, lock, lockadagen. Integer 0. 127.0.0.1:6379. GET user, sign up, lock, locked. Setx key, seconds value, set with e expiration. This command sets the value of key and also sets its time to live, TTL, in seconds. It's a shorthand for set followed by expire and is an atomic operation, meaning both the set and the expiration are guaranteed to happen together. This is extremely important for caching scenarios. PSETX key, milliseconds value. Similar to SETEX, but the TTL is specified in milliseconds. 127.0.0.1:6379. SETX session. User. 12360. User session data. OK. 127.0.0.1:6379. TTL session. User. 123. Integer 58. 127.0.0.1:6379. GET session. User. 123. User session data. Wait 61 seconds. 127.0.0.1:6379. GET session. User. 123. Nil. MSCT key 1 value 1 key 2 value 2. Multiple set. Sets multiple key value pairs atomically. This means either all of the operations succeed or none of them do. This can also improve performance by reducing the number of round trips to the Redis server. MGET key 1 key 2, multiple get, returns the values of all specified keys. For every key that does not hold a string value or does not exist, nil is returned. 127.0.0.1:6379. MSCT user, name, Charlie user. Email charlie@example.com. OK. 127.0.0.1:6379. MGT user, name user, email user, phone. 1. Charlie. 2. charlie@example.com. 3. Nil. Numeric operations on strings. One of Redis's clever features is its ability to treat string values as integers or floats for arithmetic operations, as long as the string content represents a valid number. This allows you to use Redis strings for counters, rate limits, and unique ID generation. INCR key increments the number stored at key by 1. If the key does not exist, it is set to 0 before performing the operation. If the string value is not an integer, an error is returned. INCRBY key increment increments the number stored at key by the specified increment. DECR key, DECRBY key decrement. Analogous to INCR and INCRBY, but for decrementing. INCRBY float key increment increments the number stored at key by the specified increment, which can be a floating point number. If the key does not exist, it is set to 0.0 before. 127.0.0.1:6379, set page, views, homepage 0. OK. 127.0.0.1:6379, INCR page, views, homepage. Integer 1. 127.0.0.1:6379, INCR page, views, homepage. Integer 2. 127.0.0.1:6379, INCRBY page, views, homepage 10. Integer 12. 127.0.0.1:6379, INCRBYFLOET stock, price, Apple 0.5. 0.5. 127.0.0.1:6379, INCRBYFLOET stock, price, Apple 1.25. 1.75. These operations are atomic, meaning multiple clients can INCR a key safely without worrying about race conditions, resulting in incorrect counts. This is a critical feature for building reliable counters and tracking metrics. Appending and substring operations. Redis strings also support operations that modify parts of a string or retrieve substrings. Append key value. Appends the value to the string stored at key. If key does not exist, it is created and set as if set key value was called. Returns the length of the string after the append operation. 127.0.0.1:6379, set greetings, hello. OK. 127.0.0.1:6379, append greetings, world. Integer 11. 127.0.0.1:6379, GET greetings. Hello world. strlen key. Returns the length of the string value stored at key. Returns if the key does not exist. 127.0.0.1:6379, strlen greetings. Integer 11. gtrng key start end. Returns the substring of the string value stored at key, determined by the start and end offsets, inclusive. Negative offsets can be used to specify offsets from the end of the string, where -1 is the last character, -2 is the second to last, and so forth. setrang key offset value. Overwrites part of the string stored at key, starting at the specified offset with value. If offset is larger than the current string length, the string is padded with null bytes, \x00, to reach the offset before value is inserted. 127.0.0.1:6379, set my message, hello Redis. OK. 127.0.0.1:6379, gtrng my message, 610. Redis. 127.0.0.1:6379, setrng my message 6, world. Integer 11. 127.0.0.1:6379, get my message. Hello world. Bitmaps treating strings as bit arrays. One of the more advanced and powerful uses of strings is to treat them as bit arrays or bitmaps. Since a Redis string is a binary-safe sequence of bytes, each byte consists of 8 bits. This allows you to set or get individual bits within a string, effectively turning it into a very compact data structure for specific use cases. The maximum size of a string, 512 MB, translates to roughly 4 billion individual bits. setbit key offset value. Sets or clears the bit at offset in the string value stored at key. Value must be either 0 or 1. Returns the original bit value stored at offset. If the string is shorter than offset, it's extended with null bytes, \x00. getbit key offset. Returns the bit value at offset in the string value stored at key. bitcount key start end. Counts the number of set bits, bits with value 1, in the string. You can optionally specify a start and end byte offset to count bits within a specific range. bitop operation disci key 1 key 2 performs a bitwise operation and OR, XOR, not between one or more keys, and stores the result in disci. Use cases for bitmaps. User online status. You could have a user online bitmap. When a user logs in, setbit user online userid1. When they log out, setbit user online userid0. bitcount user Online would give you the number of currently online users. Tracking unique visitors over time. For tracking daily unique visitors, you could use setbit daily, unique, visitors, date userid 1. If userid is an ever-increasing integer, this is extremely memory efficient. Bitcount daily, unique, visitors, date tells you how many unique visitors there were on that day. Feature flagging. A bitmap could store which users have access to a new feature. Example, tracking user logins. 127.0.0.1:6379 setbit users. Active, today 101 hash user 100 logged in. Integer 0. 127.0.0.1:6379 setbit users. Active, today 205 1 hash user 205 logged in. Integer 0. 127.0.0.1:6379 getbit users. Active, today 100. Integer 1. 127.0.0.1:6379 bitcount users. Active today hash how many active users. Integer 2. String expiration and TTL. Expiration is a powerful feature in Redis that allows keys to automatically disappear after a certain amount of time. This is invaluable for managing transient data like caches, sessions, or temporary tokens. Expire key seconds. Sets a timeout on key in seconds. After the specified time, the key will automatically be deleted. Returns 1 if the timeout was set, 0 if the key does not exist or the timeout could not be set. Pxbre key milliseconds. Similar to expire, but the timeout is in milliseconds. TTL key / PTTL key. Returns the remaining time to live of a key in seconds, TTL, or milliseconds, PTTL. Returns TTL if the key has an expiry set. Returns if the key exists but has no associated expiry. Returns if the key does not exist. Persist key. Removes the existing timeout on key, effectively making it permanent. Returns 1 if the timeout was removed, 0 if the key does not exist or has no associated timeout. 127.0.0.1:6379 set page, cache, homepage 8 content. OK. 127.0.0.1:6379 expire page, cache, home 300 hash cache for 5 minutes. Integer 1. 127.0.0.1:6379 TTL page, cache, home. Integer 298. 127.0.0.1:6379 persist page, cache, home hash remove expiration. Integer 1. 127.0.0.1:6379 TTL page, cache, home. Integer. How expiration works with persistence. When Redis persists data to disk, which we'll cover in a later chapter, keys with expiration times are also saved with their remaining TTL. Upon restart, Redis recalculates their expiration times, ensuring they expire at the correct moment. Practical use cases for strings. Let's look at how Redis strings are applied in common development scenarios. A simple caching, cache-aside pattern. Caching is one of the most frequent uses of Redis strings. The cache-aside pattern is widely adopted. An application tries to fetch data from Redis the cache. If the data is found, a cache hit, it's returned immediately. If the data is not found, a cache miss, the application fetches it from the primary data source, e.g., a database. The retrieved data is then stored in Redis with an expiration for future requests before being returned to the application. Conceptual application logic. Function getProductDetails, producted. 1. Try to get from cache. Cache data equals Redis get, product, plus producted. If cache data is not null, return cache data. 2. Cache miss, fetch from database. DB data, database fetch product, producted. 3. Store in cache for future requests, e.g., 5 minutes expiration. Redis setx, product, plus producted, 300 DB data. 4. Return data. Return DB data. The setx command is perfect here because it atomically sets the value and its expiration, preventing a brief window where the key might exist without a TTL. B. User sessions with expiration. Managing user sessions in stateless applications, like microservices, is another perfect fit for Redis strings. When a user logs in, a unique session ID is generated, and a string containing relevant user data, user ID, roles, preferences, is stored in Redis under that session ID as the key, with an expiration time. Conceptual application logic, function loginuser, username, password, authenticate user against database. If authentication successful, sessionid equals generatuniquoid, session data equals JSON encode, userid, username, user.username, roles, user roles. Store session data in Redis for 30 minutes. Redis setx session, plus sessionid 1800 session data. Return sessionid. LC. Return null. Function validate session, sessionid. Retrieve session data. Session data equals Redis get, session, plus sessionid. If session data is not null, optionally, extend session expiration on activity. Redis expire session, plus sessionid 1800, reset TTL. Return JSON.decode, session data. LC. Return null session expired or invalid. See page view counters. Tracking simple metrics like page views is easily done with INCR. On every page load for About Us. Redis.anchor, page views/About Us. To get total views, Redis get, page views/About Us. This is highly efficient and thread-safe due to Redis's atomic operations. Distributed atomic counters. INCR is not just for page views. It can be used for any scenario where you need a globally unique, incrementing ID or an atomic counter shared across multiple application instances. For example, generating sequential invoice numbers. Call this function from any application instance to get the next invoice number. Function getNextInvoiceNumber. Return Redis.anchor, global invoice number. Each call guarantees a unique, monotonically increasing number without race conditions, making Redis strings a powerful tool for maintaining distributed state. Strings are the fundamental building blocks of Redis and a testament to its flexibility and performance. While simple, they enable a vast array of common application patterns. In the next chapter, we'll build on this foundation by exploring hashes, which allow you to store more structured, object-like data within a single Redis key. Organizing complexity. Hashes for structured data. In the previous chapter, we explored Redis strings, the most basic way to store a single piece of binary-safe data under a unique key. While incredibly powerful for simple key-value pairs, what if you need to store more complex, structured data? Imagine a user profile with a name, email, and age, or a product entry with a name, description, and price. Storing each of these attributes as separate string keys, e.g., user, 123, name, user, 123, email, user, 123. Age works, but it can quickly lead to a cluttered key space and require multiple Redis calls to retrieve all related data for a single entity. This is where Redis hashes come into play. Introduction to Redis hashes. A Redis hash provides a perfect way to represent structured objects or records. Conceptually, a hash is a mapping between string fields and string values, much like a hash map, dictionary, or object in most programming languages. Each hash is stored under a single key, and within that key, you can store numerous field value pairs. Think of it like this: string keys. User 123, name, Alice, user 123, email, alice@example.com. Hash key. User 123, name, Alice, email, alice@example.com, age, 30. The benefits of using hashes for structured data are significant. Organized key space. All related attributes of an entity are grouped under a single, meaningful key, e.g., user 123. This keeps your Redis key space cleaner. Reduced memory consumption. For many small field value pairs, hashes are generally more memory efficient than storing each field as a separate string key. Redis internally optimizes small hashes. Atomic operations on fields. You can atomically update, increment, or retrieve individual fields within a hash without affecting other fields. Fewer network round trips. You can retrieve all or multiple fields of an object in a single network call, reducing latency compared to fetching multiple individual string keys. A Redis hash can store up to approximately 232 one-field value pairs, making it virtually unlimited for practical purposes. Basic hash commands. Let's explore the fundamental commands for managing Redis hashes. HSET key field value field to value 2. This is the primary command to set fields within a hash. It sets the value associated with field in the hash stored at key. If key does not exist, a new hash is created. If field already exists, its value is overwritten. You can set multiple field value pairs in a single HSET command, which is very efficient. The command returns the number of fields that were newly added. If you update existing fields, they are not counted towards this number. 127.0.0.1:6379 HSET user. Profile. 100 name Bob, email bob@example.com. Integer 2. 127.0.0.1:6379 HSET user. Profile. 100 age 25. Integer 1. 127.0.0.1:6379 HSET user. Profile. 100 email robert@example.com. Integer 0. HGET key field. Retrieves the value associated with field in the hash stored at key. If key does not exist, or field does not exist within the hash, it returns nil. 127.0.0.1:6379 HGET user. Profile. 100 name. Bob. 127.0.0.1:6379 HGET user. Profile. 100 email. robert@example.com. 127.0.0.1:6379 HGET user. Profile. 100 phone. Nil. HGTLLT. Returns all field value pairs of the hash stored at key. The response is an alternating list of fields and their corresponding values. Caution. For very large hashes, thousands or millions of fields, HGTLL can consume significant network bandwidth and block the Redis server for a short duration while it fetches all data. For large hashes where you only need to iterate, consider using HSCAN, part of the scan family of commands, which allows incremental iteration. 127.0.0.1:6379 HGTLL user. Profile. 100. 1. Name. 2. Bob. 3. Email. 4. robert@example.com. 5. Age. 6. 25. HMSET key field 1 value 1 field 2 value 2. Deprecated. This command is similar to HSET with multiple arguments, but is officially deprecated in newer Redis versions, 6.0 plus. While it still works for compatibility, it's recommended to use HSET with multiple field value arguments instead. Its return value is always okay. HMGET key field 1 field 2 retrieves the values associated with the specified fields in the hash stored at key. Missing fields return nil in their respective positions in the array. This is efficient for fetching several, but not all, fields. 127.0.0.1:6379 HMGT user. Profile. 100 name age phone. 1 Bob. 2 25. 3 nil. HDEL key field 1 field 2. Deletes one or more fields from the hash stored at key. Returns the number of fields that were actually removed. 127.0.0.1:6379 HDEL user. Profile. 108. Integer 1. 127.0.0.1:6379 HGTLL user. Profile. 100. 1 name. 2 Bob. 3 email. 4 robert@example.com. HLEN key. Returns the number of fields, key value pairs, contained in the hash stored at key. Returns if the key does not exist. 127.0.0.1:6379 HLEN user. Profile. 100. Integer 2. HXSDS key field. Checks if field exists within the hash stored at key. Returns 1 if the field exists, 0 otherwise, including if the key itself does not exist. 127.0.0.1:6379 HEXISDS user. Profile. 100 name. Integer 1. 127.0.0.1:6379 HEXISDS user. Profile. 108. Integer 0. HKYS key. returns a list of all field names within the hash stored at key. HVLS key returns a list of all values within the hash stored at key. 127.0.0.1:6379 HKEYS user profile 100. 1. Name. 2. Email. 127.0.0.1:6379 HVALS user profile 100. 1. Bob. 2. Robert@example.com. Numeric operations on hash fields. Just like with strings, Redis allows you to perform atomic numeric operations directly on the values of hash fields, provided those values represent valid integers or floats. HINCRBY key field increment increments the number stored at field in the hash at key by increment. If the field does not exist, it is created and set to 0 before the operation. The value stored must be an integer. HINCRBY key field increment increments the number stored at field in the hash at key by increment, which can be a floating point number. 127.0.0.1:6379 HSET product item ABC stock 100. Integer 1. 127.0.0.1:6379 HINCRBY product item ABC stock hash a product was sold. Integer 99. 127.0.0.1:6379 HINCRBY product item ABC views 1 hash increment views. Integer 1. 127.0.0.1:6379 HINCRBY FLOAT product item ABC rating 0.5 hash a new rating 0.5. 127.0.0.1:6379 HGTLL product item ABC 1 stock 2 99 3 views 4 1 5 rating 6 0.5. These operations are atomic and safe for concurrent access, making them perfect for managing counters or numerical values associated with entities. Practical use cases for hashes. Hashes are extremely common in modern applications due to their ability to neatly package related data. User profiles. One of the most intuitive applications for hashes is storing user profiles. Instead of having separate keys for username, user, email user, age, you can consolidate them under one user ID. Conceptual use. When a user updates their profile, Redis HSET user, profile $user ID, names, new name, email, new email, bio. New bio. When fetching a user's complete profile, user profile equals Redis HGetAll user, profile, $user ID. When a user changes their password, a field update, Redis HSET user, profile $user ID. Password hash, new password hash. This approach keeps all user-specific data logically connected and makes it easy to retrieve the entire profile in one go. Product catalogs and inventory. For e-commerce or inventory systems, hashes are excellent for storing product details and even managing stock levels in near real time. Conceptual use. When adding a new product, Redis HSET product $SKU, name, widget X, price 29.99, description, stock 100. When a product is purchased, note, this needs careful handling in a real application to prevent overselling. A simpler decrement, however, is Redis Hinkeby product $SKU, stock -1. When stocking up an item, Redis Hinkeby product $SKU, stock 50. Get product details for display. Product details equals Redis HGetAll, product $SKU. Using HINCRBY for stock management offers significant performance advantages for high-volume sales compared to querying and updating a relational database. See shopping cart items. A user's shopping cart can be modeled as a hash. The main key would be the user session ID or user ID, and each field represents a product TID with its corresponding quantity value. Conceptual use. User adds item to cart. Redis Hinkeby cart $session ID, product 123, 1 increment quantity for product 123. Redis Hinkeby cart $session ID, product 456, 2 user wants 2 of product 456. User removes item. Redis HDEL cart $session ID, product 123. Get all items in cart. Cart items equals Redis HGetAll cart $session ID. When to use hashes versus strings. The choice between a simple string key for each attribute and grouping them in a hash often comes down to how conceptually related the data is and how you intend to access it. Feature/scenario, use strings, individual keys. Use hashes, single key with fields. The data relationship. Each piece of data is largely independent, e.g., page, views, home. Data represents attributes of a single logical entity, e.g., user, 100. Retrieval strategy, fetch individual values, get. Can MGET many disparate keys. Fetch all fields, HGTLL, or several specific fields, HMGT. Key space management, potentially many individual keys. Fewer top-level keys, but more logical structure. Memory efficiency, less efficient for many small, related key-value pairs, more overhead per key. More efficient for grouping several small related field, value pairs. Atomic operations, INCR, DECR, append on single values. HINCRBY, HSET on specific fields within an entity. Primary use cases, caching large blobs, simple counters, session tokens. User profiles, product details, configuration, shopping carts. In summary, hashes allow you to store structured data efficiently and logically within Redis, reducing key space clutter and enabling atomic operations on individual attributes of an object. They are a fundamental data type for building robust and performant applications that deal with complex entities. In the next chapter, we'll shift our focus to Redis lists, powerful data structures ideal for ordered collections, message queues, and other sequential data patterns. Sequential powerhouses, list for queues and stacks. So far, we've explored strings for simple key-value pairs and hashes for structured object-like data. What if you need an ordered collection of items, where the sequence matters, and you frequently need to add or remove items from either end? Think about a job queue, a user's recent activity feed, or a log of events. For these scenarios, Redis provides the list data type. Introduction to Redis lists. A Redis list is an ordered collection of string elements. It's essentially a linked list, meaning that adding or removing elements from either the head, left, or the tail, right of the list is a constant time operation, O1. This makes Redis lists extremely efficient for implementing queues and stacks. Unlike arrays in many programming languages, Redis lists are optimized for operations at their ends. Accessing elements by index in the middle of a very long list, LINDEX, or trimming a range, LTRIM, can be slower, with a complexity proportional to the distance from the ends or the size of the range, respectively. However, for typical queue and stack patterns, lists are blazingly fast. The elements within a Redis list are simply strings. A single Redis list can hold up to 232.1 elements, which is practically unlimited. Basic list commands. The most fundamental list operations involve adding and removing elements from the ends. LPUSH key value, left push. Adds one or more values to the head, left side of the list stored at key. If key does not exist, it's created as an empty list before the push operation. Returns the length of the list after the push operation. RPUSH key value, right push. Adds one or more values to the tail, right side of the list stored at key. Similar to LPUSH in behavior for non-existent keys. Returns the length of the list. 127.0.0.1:6379 RPUSH mylist, first item. Integer 1. 127.0.0.1:6379 LPUSH mylist, new first item. Integer 2. 127.0.0.1:6379 RPUSH mylist, last item. Integer 3. After these commands, mylist would conceptually look like new first item, last item, LPOP key left pop. Removes and returns the first element from the head left side of the list stored at key. If the list is empty, it returns nil. RPOP key right pop. Removes and returns the last element from the tail right side of the list stored at key. Returns nil if the list is empty. 127.0.0.1:6379 LPOP mylist. New first item. 127.0.0.1:6379 RPOP mylist. Last item. Now mylist contains only first item. blocking list commands for message queues. While LPOP and RPOP are synchronous, they return immediately, even if the list is empty. Redis provides blocking versions that wait for elements to become available. This is crucial for building robust message queues where consumer processes need to wait for new jobs without constantly polling. BLPOP key, timeout, blocking left pop, removes and returns the first element from the first non-empty list among the keys provided. If no elements are available in any of the specified lists, the command blocks the connection until an element becomes available or the timeout in seconds is reached. A timeout of 0 means it blocks indefinitely. Returns nil if the timeout is reached. BRPOP key, timeout blocking right pop, similar to BLPOP, but removes and returns the last element from the list. In one Redis CLI window, consumer waiting for a message, 127.0.0.1:6379, BLPOP MyQ0. This window will now block. In another Redis CLI window, producer adds a message, 127.0.0.1:6379, RPUSH MyQ. Process this job. Integer 1. The first Redis CLI window will immediately unblock and display 1 MyQ. 2. Process this job. BLPOP and BRPOP are fundamental for durable distributed work queues, offering simple, reliable messaging. Other useful list commands. Beyond basic end operations, Redis lists offer other ways to inspect and manipulate their contents, though these tend to be less efficient for very large lists as they might involve traversing elements. LLEN key, listlen_gth, returns the length of the list stored at key. Returns if the key does not exist. 127.0.0.1:6379, LLEN mylist. Integer 1. LRNG key start stop, list range, returns the specified elements of the list stored at key. Start and stop are zero-based indices. Negative indices can be used to specify offsets from the end of the list, where -1 is the last element, -2 is the second to last, and so forth. LRANG is often used to retrieve all elements of a list, e.g., LRANG mylist 0-1. 127.0.0.1:6379, RPUSH tasks, task 1, task 2, task 3, task 4. Integer 4, 127.0.0.1:6379, LRANG task 0. 1 task 1, 2 task 2, 3 task 3, 4 task 4, 127.0.0.1:6379, LRANG tasks 1 2. 1 task 2, 2 task 3, LINDX key index, returns the element at index in the list stored at key. Returns nil if the index is out of range. 127.0.0.1:6379, LINDX tasks 0. Task 1, 127.0.0.1:6379, LINDX tasks 99. Nil, LREM key count value, list remove. Removes the first count occurrences of value from the list stored at key. If count is positive, it removes elements starting from the head. If count is negative, it removes elements starting from the tail. If count is 0, it removes all occurrences of value. Returns the number of removed elements. 127.0.0.1:6379, RPUSH mylist A, B, C, A, D. Integer 5, 127.0.0.1:6379, LREM mylist 1A. Integer 1, 127.0.0.1:6379, LRANG mylist 0-1. 1's B, 2C, 3A, 4D, LINSRT key before after pivot value. Inserts value into the list stored at key before or after the pivot element. Returns the new length of the list, or if pivot was not found. LSET key index value. Sets the element at index in the list stored at key to value. An error is returned if index is out of range. RPOPLPUSH, source destination. Atomically removes the last element from source list and pushes it to the front of the destination list. This command is incredibly useful for implementing reliable job queues and circular lists. Imagine a queue of jobs. 127.0.0.1:6379 RPUSH pending jobs, job 1, job 2, job 3. Integer 3. A worker takes a job from pending jobs and puts it into processing jobs. If the worker crashes, the job is still in processing jobs and can be requeued. 127.0.0.1:6379 RPOPLPUSH pending jobs processing jobs. Job 3. 127.0.0.1:6379 LRANG pending jobs. 1. Job 1. 2. Job 2. 127.0.0.1:6379 LRANG processing jobs. 1. Jobs 3. This pattern allows for a degree of fault tolerance. If a worker crashes before completing a job, the job is not lost from the queue. It's simply stuck in processing jobs and can be moved back to pending jobs after a timeout or manual intervention. Practical applications of lists. Redis lists are powerful for managing ordered sequences of data, making them ideal for several common patterns. A queues, FIFO, first in, first out. The most classic use of lists is for message queues. Producers RPUSH messages onto the tail of a list, and consumers LPOP them from the head. Conceptual queue pattern. Producer. Application publishes a job to the queue. Redis rpush, custom order queue, ordered 456. Consumer. Application worker waits for a job. Job equals Redis BL pop. Custom order queue, 0, blocking pop, waits indefinitely. If job is not null. Process order, job value. This model is highly efficient for distributing tasks to multiple workers, enabling asynchronous processing and decoupling components of your application. B. Stacks LIFO last in, first out. While less common than queues, lists can easily function as stacks. Both LPUSH LPOP and RPUSH RPOP pairs implement stack behavior. Conceptual stack pattern. Push onto stack. Redis lpush, user recent live pages, products widget A. Redis lpush, user recent live pages, checkout. Pop from stack e.g., back button. Page equals Redis lpop, user recent live pages. This keeps the most recent item at the top head of the stack. See message buffering bounded lists. Lists can act as buffers for events or logs, especially when you only care about the most recent n items. LTRIM allows you to maintain a fixed size list by trimming elements outside a specified range. Conceptual bounded list. User performs an action. Redis lpush, user activitalog 123, loginit 0. Redis lpush, user activitalog 123. Viewed product XYZ. Redis lpush, user activitalog 123, added item to cart. Keep only the 100 most recent activities. Redis ltrim, user activitalog 123, 099. Keep elements from index 0 to 99. This means older log entries are automatically discarded once the list exceeds 100 items, saving memory and keeping the data relevant. Decircular lists and retry queues. As demonstrated with RPOPLPUSH, this command is excellent for circular buffers round robin, a list of items to process in a loop. Retry queues. If a job fails, move it from processing jobs back to pending jobs or a retry queue using RPOPLPUSH. This ensures jobs are not lost even if a worker fails. Summary. Redis lists are powerful sequential data structures perfect for FIFO queues, LIFO stacks, event logs, and message, passing between different parts of a distributed system. Their atomic push and pop operations, especially the blocking variants, BLPOP, BRPOP, make them simple yet robust for building asynchronous processing workflows. Building on the concept of collections, in the next chapter, we will explore Redis sets, which allow you to store unordered collections of unique elements and perform various set operations like unions and intersections. Unique collections, sets for membership and relationships. We've covered strings for single values, hashes for structured objects, and lists for ordered sequences. Now, let's explore a data type that concerns itself with groups of unique, unordered items, Redis sets. Sets are fundamental for tasks involving membership checking, preventing duplicates, and performing mathematical set operations like unions and intersections. Introduction to Redis sets. A Redis set is an unordered collection of unique strings. This means two important things. Uniqueness. Every element added to a set must be distinct. If you try to add an element that already exists in the set, Redis simply ignores the operation, and the set remains unchanged. This property makes sets perfect for ensuring that you only store distinct items. Unordered. The elements within a set do not have a defined order. When you retrieve all members of a set, the order in which they are returned is not guaranteed and can vary over time. If you need order, you should consider a list or a sorted set. Like other Redis data types, the elements within a set are binary safe strings, and a set can hold up to 232 members, making it suitable for very large collections. Sets are incredibly efficient for checking if an element is already a member, often performing this check in O(1) constant time due to their underlying hash table implementation. Basic set commands. Let's look at the core commands for manipulating Redis sets. Sadd key member set add. Adds one or more members to the set stored at key. If key does not exist, a new empty set is created. Existing members are ignored. Returns the number of members that were actually added, i.e., not already present. 127.0.0.1:6379 SADD Programming Languages Python, Java, C++. Python. Integer 3. In this example, Python was added only once, so the count is 3, not 4. SMEMBRS key, set members. Returns all members of the set stored at key. The order is not guaranteed. 127.0.0.1:6379 SMEMBRS Programming Languages. 1. Java. 2. C++. 3. Python. The order here might be different on your machine or on subsequent calls. SISMEMBR key member, set is member. Checks if member is a member of the set stored at key. Returns 1 if the member exists, 0 otherwise, including if the key does not exist. This is a very fast operation, making sets ideal for membership testing. 127.0.0.1:6379 SISMEMBR Programming Languages Python. Integer 1. 127.0.0.1:6379 SISMEMBR Programming Languages JavaScript. Integer 0. SREM key member set remove. Removes one or more members from the set stored at key. If a member does not exist in the set, it is ignored. Returns the number of members that were actually removed. 127.0.0.1:6379 SREM Programming Languages C++. PHP. Integer 1. 127.0.0.1:6379 SMEMBRS Programming Languages. 1. Java. 2. Python. SCARD key, set cardinality. Returns the number of members, cardinality, of the set stored at key. Returns if the key does not exist. 127.0.0.1:6379 SCARD Programming Languages. Integer 2. Set operations, intersections, unions, and differences. One of the most powerful features of Redis sets is their ability to perform mathematical set operations directly on the server. This allows for complex filtering and relationship queries with minimal network overhead. Center key, set in TR section. Returns the members present in all the specified sets. 127.0.0.1:6379 SADD Developers. Backend Alice, Bob, Charlie, Frank. Integer 4. 127.0.0.1:6379 SADD Developers. Frontend Charlie, David, Alice, Eve. Integer 4. 127.0.0.1:6379 Sinter Developers. Backend Developers. Frontend. 1. Alice. 2. Charlie. These are the developers working on both backend and frontend. SINTRSTORE destination key computes the intersection of all the specified sets and stores the result in destination. Returns the number of elements in the resulting set. This is efficient if you need to reuse the intersection result multiple times. SUNION key, set union. returns the members present in at least one of the specified sets, the combined unique members from all sets. 127.0.0.1:6379 SUNION developers, backend developers, frontend. 1 Bob, 2 Eve, 3 Charlie, 4 David, 5 Frank, 6 Alice. These are all unique developers involved in backend or frontend. SUNIONSTORE destination key computes the union of all the specified sets and stores the result in destination. SDIFF key set diff variance returns the members present in the first set that are not present in any of the subsequent sets. Think of it as set 1, set 2 plus set 3 plus. 127.0.0.1:6379 SDIFF developers, backend developers, frontend. 1 Bob, 2 Frank. These are developers who work on backend, but not frontend. 127.0.0.1:6379 SDIFF developers, frontend developers, backend. 1 Eve, 2 David. These are developers who work on frontend, but not backend. SDIFF STORE destination key computes the difference of the specified sets and stores the result in destination. Random element retrieve. Sets also provide commands for retrieving random elements without necessarily removing them. SRANDMEMBR key count, set random member, returns a random member from the set. If count is positive, it returns an array of count unique random members. If count is negative, it returns an array of abs, count, random members, possibly with duplicates. 127.0.0.1:6379 SRANDMEMBR developers, backend. Frank, 127.0.0.1:6379 SRANDMEMBR developers, backend 2. 1 Frank, 2 Bob. SBOP key count, set pop, removes and returns a random member from the set. If count is specified, it removes and returns count unique random members. If the set becomes empty after the operation, the key is automatically deleted. 127.0.0.1:6379 SBOP developers, frontend 2. 1 David, 2 Eve. 127.0.0.1:6379 SMEMBRS developers, frontend. 1 Charlie, 2 Alice. SBOP is often used for tasks like drawing a lottery winner or getting a random item from a pool, ensuring it's not picked again unless explicitly re-added. Practical use cases for sets. Redis sets are incredibly versatile and are used in many common application patterns. A unique visitors tracking. This is a classic use case. If you need to count the unique visitors to a web page or feature over a period, e.g., daily unique visitors, a Redis set is perfect. Each visitor's ID is SADD'd to a set keyed by the date. Conceptual use. When a user visits a page, user-id is unique per user. Redis SAD, unique visitors, 2023 to 10 to 26, user 101, user 102, user 101, user 1 when added only once. To get the count of unique visitors for the day, unique count equals Redis SCARD. Unique visitors, 2023 to 10 to 26, will return 2. To calculate unique visitors across multiple days or periods, you could use SUNION on multiple daily sets. For very large-scale unique counting, also consider Redis's hyperlog log, covered in a later chapter, which provides approximate unique counts using significantly less memory. B. Tagging systems. Sets are ideal for implementing tagging functionality where items, articles, products, photos can have multiple tags, and you need to find items associated with specific tags. Conceptual use. When saving an article with tags, Redis SAD, article 123 tags, technology, AI, programming. Redis SAD, article 456 tags, web dev, programming, JavaScript. Find all articles tagged, programming. This is a simplified example, often involves an inverted index. You might have a set for each tag, containing article IDs for retrieval. Redis SAD, tag programming articles, 123, 456. Redis SAD, tag AI articles, 123. to find articles that are tagged both programming and AI. Redis Center tag programming articles. Tag AI articles returns 123. C. Social network relationships, followers following. Sets are a natural fit for modeling social network relationships like followers and following. Conceptual use. User A follows user B. Redis SAD, user A following user B. Redis SAD, user B followers user A. User B follows C. Redis SAD, user B following user C. Redis SAD, user C followers user B. Check if user A follows user B. Redis sysmember user A following user B. Get all followers of user B. Redis members user B followers. Get people user A follows who also follow user D. Mutual friends query like. Redis Center user A following user D followers. D. Access control lists, ACLS permissions. You can use sets to store roles or permissions assigned to users or groups, making it easy to check if a user has a specific permission. Conceptual use. Define user roles. Redis SAD, user 101 roles, admin, editor. Redis SAD, user 102 roles, viewer. Check if user 101 has the admin role. Redis sysmember user 101 roles, admin returns 1. Sets provide efficiency in storing unique items and powerful server-side operations for deriving relationships between them. These capabilities make them indispensable for a wide range of applications that rely on membership, filtering, and graph-like structures. In the next chapter, we'll build on the concept of ordered data by diving into sorted sets, which combine the uniqueness of sets with an associated score, allowing for efficient ordering and ranking. Ordered precision, sorted sets for rankings and timelines. We've explored how Redis lists provide ordered collections and how sets manage unique, unordered elements. What if you need a collection that is both unique and ordered, but where the order isn't determined by insertion time, but by some numerical value? This is precisely the problem that Redis sorted sets solve, making them ideal for scenarios involving leaderboards, score-based rankings, and time-ordered data. Introduction to Redis sorted sets, ZSETs. A Redis sorted set, often called a ZSET, is a collection of unique members where each member is associated with a numerical score. The members are stored in a sorted order based on their scores, from lowest score to highest. If members have identical scores, they are then sorted lexicographically, alphabetically, by their member strings. Key characteristics, uniqueness. Like regular sets, every member in a sorted set must be unique. You cannot have duplicate members. Order by score. The primary ordering mechanism is the associated numerical score. This allows for quick retrieval of elements by rank, e.g., top 10, bottom 5. Efficient lookups. Sorted sets provide fast access to elements by their member value, by their score range, and by their rank position in the sorted list. The elements within a sorted set are binary safe strings, and the scores are double precision floating point numbers. A sorted set can hold up to 232 members. Internally, Redis uses a combination of a hash table for fast lookups of members and their scores, and a skip list for maintaining the sorted order and fast range queries. Basic sorted set commands. Let's look at the fundamental commands for manipulating Redis sorted sets. ZADD key NX Roman 20, CH inker, score member score 2 member 2, sorted set ADD. Adds one or more member score pairs to the sorted set stored at key. If key does not exist, a new empty sorted set is created. If member already exists, its score is updated to the new score, and its position in the set is readjusted. Returns the number of members that were actually added, i.e., not already present or whose score was updated. Options, NX, only add new elements, don't update existing scores. XX, only update existing elements, don't add new elements. CH, returns the number of members whose score was changed, including new additions and updates, rather than just new additions. INCR, increments the score of a member by the given score value, similar to ZINCRBY, making ZADD INCR equivalent. 127.0.0.1:6379 ZADD leaderboard 100, player A, 150 player B, 75 player C. Integer 3, 127.0.0.1:6379 ZADD leaderboard 120, play array, hash play arrays score updates. Integer 0. ZRANGE key start stop with scores, sorted set range. Returns the elements within the specified start and stop ranks, 0 indexed. The members are returned in ascending order of their scores. Start and stop are ranks, not scores. 0 is the lowest score, -1 is the highest. WITHSCORES option returns members along with their scores. 127.0.0.1:6379, ZRANGE leaderboard -1 WITHSCORES. 1. Player C. 2. 75. 3. Player A. 4. 120. 5. Player B. 6. 150. ZRANGE key start stop with scores. Sorted set reverse range. Similar to ZRANGE, but returns elements in descending order of their scores. 0 is the highest score, -1 is the lowest. 127.0.0.1:6379, ZRANGE leaderboard 0, 1 WITHSCORES. 1. Player B. 2. 150. 3. Player A. 4. 120. This is perfect for leaderboards e.g., top-end players. ZRANK key member, sorted set rank. Returns the 0 indexed rank of member in the sorted set, with scores ordered from low to high. Returns nil if the member does not exist. ZRANK key member, sorted set reverse rank. Returns the 0 indexed rank of member in the sorted set, with scores ordered from high to low. 127.0.0.1:6379, ZRANK leaderboard play array. Integer 1. 127.0.0.1:6379, ZRANK leaderboard play array. Integer 1. Both return 1 because play array is second from lowest and second from highest in our example set. C 75, A 120, B 150. ZSCORE key member. Returns the score of member in the sorted set. Returns nil if the member does not exist. 127.0.0.1:6379, ZSCORE leaderboard play array. 120. ZINCRBY key increment member, sorted set INC remit by. Increments the score of member in the sorted set by increment. If member does not exist, it's added with score set to increment. Returns the new score. 127.0.0.1:6379, ZINCRBY leaderboard 50, play array. 170. 127.0.0.1:6379, ZRANG leaderboard -1 WITHSCORES. 1. Player A. 2. 170. 3. Player B. 4. 150. 5. Player C. 6. 75. Notice player A has now moved to the top. This operation is atomic and safe for concurrent updates. ZCARD key, sorted set cardinality, returns the number of members in the sorted set. 127.0.0.1:6379, ZCARD leaderboard. Integer 3. ZCONT keymin max. Returns the number of members in the sorted set with scores within the specified range min, max, inclusive. You can use for exclusive bounds, e.g., 100 means greater than 100. Inf and plus inf can be used for unbounded ranges. 127.0.0.1:6379, ZCOUNT leaderboard 100-160. Integer 1. 127.0.0.1:6379, ZCOUNT leaderboard 75 plus inf. Integer 3. ZRANGBUSCORE keymin max with scores, limit offset count. Returns all members of the sorted set with scores between min and max, inclusive. Members are ordered by score in ascending order. Limit can be used for pagination. ZRANGBUSCORE key max min with scores, limit offset count. Similar to ZRANGBUSCORE, but returns members in descending order of scores. Note that max and min arguments are swapped to reflect the reverse order. These range commands are excellent for retrieving nearby items, finding elements within a certain price range, or fetching events within a time window. ZREM key member, sorted set remove. removes one or more members from the sorted set. 127.0.0.1:6379 ZREM leaderboard, player B. Integer 1. 127.0.0.1:6379 ZCARD leaderboard. Integer 2. Complex sorted set operations. Aggregation. Redis allows you to perform advanced operations on multiple sorted sets, combining or intersecting them based on their scores. This is powerful for advanced filtering and aggregation. ZUNIONSTORE destination numkeys key weights weight aggregate sum min max computes the union of numkeys sorted sets specified by key arguments and stores the result in destination. If a member exists in multiple source sets, its score is aggregated. WIGHTS multiplies the score of each member in the input sets by a specified weight before aggregation. Aggregate defines how scores are combined for common members: sum, default, min, or max. ZINTRSTORE destination numkeys key weights weight aggregate sum min max, similar to ZUNIONSTORE, but computes the intersection of numkeys sorted sets. Members only appear in the result if they are present in all input sets. These commands can be used for scenarios like combining different types of engagement, likes, comments, views, into a single trending score for posts, finding common users across different game leaderboards and summing their scores. Practical use cases for sorted sets. Sorted sets are incredibly versatile for ranking and ordered data needs. A. Leaderboards and gaming. This is the quintessential use case for sorted sets. Players are members and their scores are their scores. Conceptual use. User finishes a game, update score. Redis ZAD, game leaderboard level 1, new score, user it. Display top 10 players. Top players equals Redis ZREV range, game leaderboard level 1, 0, 9. WITHSCORES. Get a player's rank. Rank equals Redis Z rank. Game leaderboard level 1, user it, +1 for one base rank. If you need to show players around a specific user, e.g., current user, top 5, bottom 5, you can use ZRANK to find their position, then ZRANGE with appropriate offsets. B. Real-time analytics dashboards, time series with scores. Sorted sets can be used to store time series data, where the score is a Unix timestamp and the member is the event data. Conceptual use. Recording a page view event. Timestamp equals current Unix timestamp. Redis ZAD, website page views metrics, timestamp. Page/home user, 123 IP, xxx.xxx.xxx.xxx. Get total page views in the last hour. 1 Arrego equals current Unix timestamp, 3600. Page views last there equals Redis Z count, website, page views metrics. 1 Arrego plus inf. Get specific events from a time reign. Recent events equals Redis Z range score, website, page views, metrics, 1 Arrego plus inf. For more complex time series data or a high volume of events, consider Redis streams, covered later. But for simple aggregation by time, sorted sets can be effective. See priority queues and task scheduling. Sorted sets can implement a priority queue where tasks are scheduled based on a priority score, e.g., timestamp when they should be processed. ZADD with a timestamp as a score, then ZRANGBYSCORE to get the next n tasks that are due. Conceptual use. Add a task to be processed at a specific Unix timestamp. Processing timestamp equals get future mstamp for task. Redis ZAD, task queue processing timestamp. Task, send a mail 123. Worker periodically checks for due tasks. Now equals current Unix timestamp. Due tasks equals Redis Z range score. Task queue, inf, now, limit, 0. 100, get up to 100 due tasks. If due tasks, process tasks. For task and due tasks, process task. Redis ZREM, task queue task, remove process task. D. Content ranking, trending topics. Articles or social media posts can be ranked by engagement, likes plus comments plus shares, with the total engagement forming the score. Whenever engagement metrics change, the score is updated with ZINCRBY, automatically re-ranking the content. Conceptual use. User likes a post. Redis Zinkaby, trending posts 1, post, article XYZ. User comments on a post. Redis Zinkaby, trending posts 2, post, article XYZ, comments might be worth more points. Display top trending posts. Trending equals Redis 0 range. Trending posts 0, 9. Sorted sets give you the best of both worlds. Unique collections, like sets, combined with inherent ordering, like lists, but based on a score criterion. This makes them incredibly powerful for any application that requires ranked data, real-time analytics dashboards, or efficient priority management. We've now covered the 5 core Redis data structures: strings, hashes, lists, sets, and sorted sets. Understanding their strengths and weaknesses is fundamental. In the next chapter, we'll move beyond individual data structures to explore how Redis provides atomic operations, efficient batch processing, and event notification mechanisms that tie these data types together in powerful ways. Atomic operations and event hooks, transactions, pipelining, and pub/sub. So far, we've explored Redis's fundamental data structures and their basic commands. But real-world applications often require more complex interactions with the database, ensuring multiple commands execute as a single, indivisible unit. Optimizing performance by sending many commands at once, or broadcasting real-time messages to connected clients. Redis provides powerful features to address these needs: transactions, pipelining, and publish-subscribe. Transactions, ensuring atomicity with multi exec and watch. In a multi-client, concurrent environment, you often need to perform a series of Redis commands as a single, atomic operation. This means either all commands in the sequence succeed or none of them do. Redis transactions provide this guarantee. The multi and exec commands are the cornerstones of Redis transactions. Multi marks the start of a transaction. All subsequent commands are queued. Exec executes all commands in the queue as a single, atomic operation. How transactions work: simple case. When multi is issued, the connection enters a transaction state. From this point until exec is called, all commands sent by the client are not executed immediately, but rather queued. When exec is called, all queued commands are executed sequentially and atomically. 127.0.0.1:6379 multi. OK. 127.0.0.1:6379 incr mycounter. Queued. 127.0.0.1:6379 lpush mylist nuitum. Queued. 127.0.0.1:6379 get mycounter. Queued. 127.0.0.1:6379 exec. 1. Integer, 1 hash result of incr mycounter. 2. Integer, 1 hash result of lpush mylist. 3. 1 hash result of get mycounter. If the client disconnects before exec is called, no commands are executed. Atomicity and isolation. Redis transactions ensure atomicity. No other client can execute commands in between the multi and exec block. This means the entire block of commands behaves as a single indivisible unit. However, Redis transactions are not full ACID. Atomicity, consistency, isolation, durability, transactions like those found in relational databases. Specifically, Redis transactions provide isolated execution, no interleaved commands, but do not fully guarantee isolation levels such as repeatable read. Once exec is called, all commands are processed, and Redis queues them without any rollback mechanism if a command itself fails, e.g., incr on a non-numeric string. If a command errors during execution, only that specific command in the queue will fail, but the rest will still execute. Watch for optimistic locking. The simple multi exec pattern is fine if you're sure no other client will modify the keys you're operating on. But what if multiple clients might try to update the same data concurrently? For example, decremented inventory in an e-commerce store needs to be done carefully. This is where Watch comes in, enabling optimistic locking. Watch allows you to monitor one or more keys before a transaction, multi. If any of the watched keys are modified by another client during the transaction, i.e., between watch and exec, the transaction's exec command will fail, returning nil. This signals to the client that the transaction needs to be retried. Scenario: inventory check and decrement. Imagine an e-commerce scenario where you want to decrement a product's stock only if it's greater than 0. Client 1 wants to buy one item of product, ABC. 127.0.0.1:6379 watch product, stock, ABC. OK. 127.0.0.1:6379 GET product, stock, ABC. 10. Meanwhile, Client 2 modifies product stock, ABC. Client 2, 127.0.0.1:6379 DECR product, stock, ABC. Integer 9. Client 1 continues. Its watched key was modified, 127.0.0.1:6379 MULTI. OK. 127.0.0.1:6379 DECR product, stock, ABC. Queued. 127.0.0.1:6379 exec. Nil hash transaction failed because product, stock, ABC was changed by Client 2. Client 1 would then retry the whole process. Watch, check stock, MULTI, DECR, exec. This optimistic locking mechanism ensures data consistency in concurrent environments without the overhead of pessimistic locks. UNW8CH can be used to clear all watch keys. Pipelining, boosting performance. Beyond atomicity, Redis's simple request-response protocol can introduce latency due to network round trips. For example, if you send 100 set commands one by one, each command incurs a network latency cost. Pipelining allows you to send multiple commands to the server in a single network request without waiting for the replies of the previous commands. Redis then queues these commands and executes them sequentially, sending back all the replies in a single response. Pipelining doesn't guarantee atomicity unless wrapped within a MULTI exec block, but it significantly reduces latency and increases throughput by batching commands. Conceptual pipelining, most client libraries handle this transparently. Instead of, command 1 goes to Redis. Redis client set, key 1, value 1. Response 1 comes back from Redis. Command 2 goes to Redis. Redis client set, key 2, value 2. Response 2 comes back from Redis. Pipelining works like all commands sent in one burst. Redis client pipeline set, key 1, value 1. Redis client pipeline set, key 2, value 2. Redis client pipeline get, key 1. Many more commands. Redis client pipeline execute, hash all commands executed, responses returned in order. The exact syntax for pipelining varies across client libraries, but the concept is universal. Batching requests to minimize network overhead. This is essential for high-performance applications that send many Redis commands in quick succession. Pipelining can lead to orders of magnitude performance improvement for high-throughput operations. Publish-subscribe pub-sub, real-time messaging. Redis's pub-sub mechanism allows clients to send and receive messages in real time without direct coupling between senders and receivers. It's a simple, fire-and-forget messaging system. Publishers send messages to specific channels. Subscribers listen for messages on specific channels. When a message is published to a channel, Redis delivers it to all currently subscribed clients on that channel. Publish channel message publishes message to channel, returns the number of clients that received the message. In one Redis CLI window, subscriber 1, 127.0.0.1:6379, subscribe news updates. Reading messages. Press Ctrl-Z to quit. 1. Subscribe. 2. News updates. 3. Integer 1. In another Redis CLI window, subscriber 2, 127.0.0.1:6379, subscribe news updates. Reading messages. Press Ctrl-Z to quit. 1. Subscribe. 2. News updates. 3. Integer 1. In a third Redis CLI window, publisher, 127.0.0.1:6379, publish news updates. Breaking. Redis is awesome. Integer 2 subscribers received the message. Both subscriber 1 and subscriber 2 windows will immediately display 1. Message. 2. News updates. 3. Breaking. Redis is awesome. Subscribe channel subscribes the client to the specified channels. Once subscribed, the client passively listens for messages. 127.0.0.1:6379 subscribe channel 1 channel 2. PSUBSCRIB pattern allows subscribing to channels using Unix-style glob patterns, e.g. chat, orders, new. If a message is published to Chat General or Chat Support, a client subscribed to chat will receive it. 127.0.0.1:6379 PSUBSCRIB user. Updates. Unsubscribe channel, PUNSUBSCRIB pattern. Unsubscribes the client from specified channels or patterns. Key characteristics of Redis PubSub, fire and forget, messages are not durable. If a client subscribes after a message is published, it will not receive that message. Redis does not store messages for later retrieval. Non-blocking for publishers. Publishers don't need to know about subscribers and don't wait for them. Real-time. Messages are delivered almost instantaneously, making it suitable for live updates, chat, and notification systems. Separate connection. When a client subscribes to channels, that specific connection enters a subscribed state and can only receive PubSub messages, and a few specific commands like ping or unsubscribe. To send other Redis commands, a separate connection is usually required. Use cases for PubSub, real-time chat applications. Users publish messages to a chat room channel, and all users subscribed to that channel receive them. Live event feeds notifications, notifying users of new activity, e.g., a new comment on their post, a new follower. Cache invalidation. When data in a database changes, a service can publish an invalidation message, and caching services listening on that channel can then clear their outdated cache entries for that data. Inter-service communication. Simple broadcast of events between microservices where complex message queuing with durability guarantees is not required. Comparing transactions, pipelining, and PubSub. While seemingly distinct, these features all contribute to building performant and responsive applications with Redis. Feature, purpose, atomicity, durability, network efficiency. Use case. Pipelining optimize network round trips, no, unless combined with MULTI, and a high many commands per trip. High throughput bulk operations. Transactions group commands atomically yes, all or nothing. NA yes, inherent pipelining, consistent updates. Optimistic locking. PubSub real-time messaging, NA no fire and forget. Yes, direct message push. Chat, live updates, event broadcasting. Understanding and effectively utilizing Redis transactions, pipelining, and PubSub can dramatically improve the reliability, performance, and real-time capabilities of your applications. In the next chapter, we'll delve into a more advanced feature, Lua Scripting, which allows you to execute complex, custom logic directly on the Redis server with full atomicity. Extending Redis. Lua Scripting for custom commands. We've seen how Redis transactions, MULTI exec with watch, offer a way to group commands for atomic execution. However, transactions have limitations. They don't allow conditional logic based on the results of previous commands within the transaction itself, and they are essentially sequential command queues. If you need complex logic, conditional execution, or computations to happen atomically and efficiently on the Redis server, you might find yourself sending multiple round trips between your application and Redis, which can introduce latency and potential race conditions. This is where Redis's built-in Lua scripting comes into play. Lua is a lightweight, high-performance scripting language, and Redis integrates it directly, allowing you to execute custom scripts on the server side. The power of Lua scripting in Redis. When you execute a Lua script in Redis, it behaves like a single atomic command. This means atomicity. All commands within a Lua script are executed as an inseparable unit. No other Redis command from any other client can be interleaved between commands within a running script. This provides strong consistency guarantees, even for complex multi-step operations. Reduced network round trips. Instead of sending multiple individual commands over the network, you send one script, which then executes all its logic directly on the Redis server. This drastically reduces network latency, especially for operations that would typically require several successive commands, e.g., read a value, perform a calculation, write a new value. Custom commands. You can essentially create your own Redis commands, encapsulating specific business logic into highly optimized, atomic server-side operations. Because Redis is single-threaded, a running Lua script blocks all other operations on the Redis server until it completes. This reinforces atomicity, but also means you should be mindful of script execution time. Long-running scripts can introduce latency for all other clients. The eval command, running scripts. You execute a Lua script using the eval command. The syntax for eval is eval script numkeys key arg. Script. This is the actual Lua script as a string. Numkeys, an integer specifying the number of keys the script will operate on. This is crucial for Redis cluster and other distributed setups to ensure all keys accessed by the script are on the same node. Key, a list of actual key names that the script will access. These keys are available within the Lua script as a global keys array, e.g., keys1, keys2, arg. A list of additional arguments, non-key arguments, that the script will use. These are available within the Lua script as a global argv array, e.g., argv1, argv2. Example: a simple get and set script. Let's illustrate with a basic script that gets a value, increments it, and sets it back. Consider the following Lua script string, which you would pass as the script argument to eval. Local current value equals redis.call get keys1. If current value equals false, then current value equals 0. And local new value equals current value plus argv1. Redis.call set keys1 new value. Return new value. Now, let's execute this using Redis CLI. 127.0.0.1:6379 eval local current value equals redis.call get keys1. If current value equals false, then current value equals 0 end. Local new value equals current value plus argv1. Redis.call set keys1 new value. Return new value 1 mycounter 10. Integer 10. 127.0.0.1:6379 get mycounter 10. 127.0.0.1:6379 eval local current value equals redis.call get keys1. If current value equals false, then current value equals 0 end. Local new value equals current value plus argv1. Redis.call set keys1 new value. Return new value 1 mycounter 5. Integer 15. 127.0.0.1:6379 get mycounter 15. Numkeys is 1 for mycounter. Keys1 refers to mycounter. Argv1 refers to the increment value 10 then 5. Redis.call is how you execute Redis commands from within Lua. This script ensures that even if mycounter doesn't exist initially, it's treated as 0 and the increment is atomic. Error handling in scripts. If a command inside redis.call returns an error, the script execution halts, and the error is returned to the client. This is different from multi-exec, where the transaction continues even if individual commands fail. Script caching and evalsha. Sending the entire Lua script string repeatedly can be inefficient, especially for larger scripts. Redis addresses this by caching executed scripts. When you eval a script, Redis calculates its SHA-1 hash and stores the script. You can then execute the script later using its SHA-1 hash instead of the whole script body via evalsha. This is generally the recommended approach for production environments. Script load script loads the script into the Redis script cache without executing it, returning its SHA-1 digest. Evalsha SHA-1 numkeys key arg executes the cached script associated with the given SHA-1. The NOSCRIPT error and fallback. If evalsha is called with a SHA-1 that Redis doesn't have in its cache, e.g., after a server restart, or if the script was never loaded, it returns a special NOSCRIPT error. Client libraries typically handle this by falling back to eval, sending the full script on the first attempt, and then using evalsha for subsequent calls once the script is known to be cached. Example using script load and evalsha. 127.0.0.1:6379 script load. Local current value equals redis.call get Keys 1. If current value equals false, then current value equals 0 end. Local new value equals current value plus argv1. Redis.call, set, keys 1, new value. Return new value. A to A to B to E to F to D to C to B to A to E to F to D to C to B to A to E to F to D to C to B to A to E to F to D to C to B to A to E to F to D to C. 2. Hash, example SHA1. Store this SHA1 in your application as a constant. 127.0.0.1:6379. EVALSHA, A to A to B to E to F to D to C to B to A to E to F to D to C to B to A to E to F to D to C to B to A to E to F to D to C to B to A to E to F to D to C. 2:1 mycounter 7. Integer 22. Script management commands. Beyond script load, Redis provides other commands for managing the script cache. Script exisds SHA1 checks if specific SHA1 hashes are present in the script cache. Script flush removes all scripts from the script cache. This is often used during development or deployments. Script kill terminates a long-running, read-only script that is currently executing if it hasn't modified the dataset yet. If the script has modified the dataset, the only option is shut down NOSAVE. Practical examples of Lua Scripting. Lua Scripting truly shines when you need to combine multiple operations into a single atomic server-side transaction. 1. Atomic INCR with expiration and conditional return. A common pattern is to increment a counter, set an expiration on it if it's new, and retrieve its value. This can be complex to do atomically with just multi exec if the expiration needs to be conditional. Script increment and expire Lua. Keys 1, the key to increment. Argv1, the increment value. Argv2, the expiration time in seconds, 0 for no expiration. Local current value equals redis.call, get. Keys 1, local new value. If current value equals false, then new value equals argv1. Start from increment value if key doesn't exist. Else, new value equals current value plus argv1. And redis.call set. Keys 1, new value. If argv2, 0, then only set expiry if argv2 is not 0. Redis.call expire keys 1, argv2. And return new value. Execution 127.0.0.1:6379 EVAL cat increment and expire Lua. 1 mycounter 160. Integer 1. 127.0.0.1:6379 TTL mycounter. Integer 59 hash will vary. This script ensures the set and expire are atomic and handles the initial state, false for non-existent key, cleanly. 2. Simple rate limiter, sliding window log. Let's implement a sliding window log rate limiter using a sorted set. The idea is to store a timestamp for each request made by a user. When a new request arrives, we remove old timestamps outside the window and then check if the number of remaining requests within the window plus the new one exceeds the limit. Script, rate limit Lua. Keys 1, the key for the user IP AG. Rate limit, user, 123. Argv1, current Unix timestamp, e.g., 1,678,886,400. Argv2, request window size in seconds, e.g., 60 seconds. Argv3, maximum number of requests allowed within the window, e.g., 100. Local key equals keys 1. Local current time equals TA number, argv1. Local window size equals TA number, argv2. Local max requests equals TA number, argv3. Local trim time equals current time window size. Remove all requests older than the window. Redis.call, zerum range abiscore. Key inf trim time. Add the current request timestamp. Redis.call zad, key current time. Get the count of requests remaining in the window. Local request count equals redis.call zcard. Set reset expiration for the key optional for cleanup. Redis.call expire key. Window size +1, keep for window size plus a bit extra. If request count less or equal max requests, then return 1 request allowed. Else, return request denied, rate limit exceeded. And execution, allow 5 requests per 60 seconds for user, 123. Current time, 1,700,000,000, example timestamp, 127.0.0.1:6379 EVAL, cat rate limit Lua. 1 rate limit, user, 123, 1,700,000,065. Integer, 1 hash request 1 allowed. 127.0.0.1:6379 EVAL, cat rate limit Lua. 1 rate limit, user. 123, 1,700,000,165. Integer, 1 hash request 2 allowed. After 5 calls, 127.0.0.1:6379 EVAL, cat rate limit Lua. 1 rate limit, user. 123, 1,700,000,565. Integer, hash request 6 denied, rate limit exceeded. This script atomically removes old entries, adds the new one, and checks the count all in one go, preventing race conditions that would occur if these steps were separate client-side operations. Benefits and considerations. Benefits: true atomicity. Scripts run to completion without interruption, ensuring data integrity for complex operations. Performance: less network overhead due to fewer round trips. Complex logic: allows conditional logic and computations directly on the server, beyond what simple multi exec can provide. Customization: effectively extends Redis with application-specific commands. Considerations: debugging. Debugging Lua scripts in Redis can be challenging. While Redis 3.2 Plus introduced a Lua debugger, it's still more complex than debugging client-side code. Blocking operations. Long-running Lua scripts will block the entire Redis server, preventing other commands from being processed. Keep scripts short and efficient to maintain Redis's responsiveness. Avoid operations like keys or network calls within scripts. Script complexity. Overly complex scripts can be harder to reason about and maintain. Balance the benefits of server-side logic with the manageability of client-side code. Memory usage. Scripts are cached in memory. While typically small, very large or numerous unique scripts could consume memory. Lua Scripting is a powerful tool in a Redis developer's arsenal, allowing the creation of highly efficient, atomic, and custom server-side procedures. When used judiciously, it can significantly enhance application performance and data consistency. In the next chapter, we'll explore streams, a relatively newer and incredibly powerful Redis data structure that brings event sourcing and durable message queues directly into Redis. Streams, the event-driven supercharger. We've already seen how Redis lists can be used to build simple message queues and how PubSub enables real-time messaging. However, these solutions have limitations. Lists lack built-in mechanisms for managing consumer groups and message acknowledgement, and PubSub is inherently fire and forget, meaning messages are not stored durably. When building modern, resilient, event-driven architectures, you often need a persistent, ordered log of events that multiple consumers can reliably process. Enter Redis streams. Introduced in Redis 5.0, streams are a powerful, append-only data structure designed specifically for high-throughput, low-latency log processing, event sourcing, and durable message queues. Introduction to Redis streams. Imagine a never-ending train track where new cars, messages, events are constantly added to the end. Each car has a unique, ever-increasing ID. Consumers, train engines, can read from any point on the track, keep track of which cars they've processed, and even form groups to collectively process the cars more efficiently. That's a good analogy for Redis streams. Key characteristics of Redis streams: append-only log. New entries are always added to the tail of the stream. They are never removed from the middle or beginning, though they can be trimmed for memory management. Unique IDs. Every entry in a stream receives a unique, auto-generated stream ID, comprising a Unix timestamp in milliseconds and a sequence number. Structured entries. Each entry is composed of one or more field value pairs, just like a Redis hash. This allows you to store structured data within each message. Consumer groups. Streams provide a built-in abstraction called consumer groups, enabling multiple client applications, consumers, to collaboratively process a stream, avoiding message duplication and tracking progress automatically. Durability and persistence. Unlike PubSub, stream messages are persistent if Redis persistence is enabled, meaning they survive server restarts. You can read messages that were published hours or days ago. These features make streams a robust alternative to specialized message brokers for many use cases, while leveraging Redis's speed and simplicity. Adding data to a stream. XADD. The XADD command is how you add new entries to a stream. Each entry is essentially a small dictionary or hash. XADD key ID field value. Key, the name of the stream. ID, the unique ID for the new entry. Asterisk, the most common option. Redis automatically generates a unique ID, guaranteed to be monotonically increasing. This ID is millisecond sequence, combining a Unix millisecond timestamp with a sequence number, which increments if multiple entries are added within the same millisecond. Specific ID, asterisk, you can provide a specific ID, but it must be greater than the last entry's ID, or Redis will return an error. This is primarily for specific recovery scenarios. Field value. One or more field value pairs that make up the entry's content. Add a sensor reading to sensor data stream. 127.0.0.1:6379, XADD sensor data sensored 1 temp, 24.5 hum 60.1, 1,700,678,400,000 to 0. Hash the auto-generated ID. Add another entry, 127.0.0.1:6379, XADD sensor data sensored 2 temp, 25.0 hum 61.2, 1,700,678,400,000 to 1 hash. Note the sequence number increment. The client receives the auto-generated ID, which can then be used to reference the entry later. Trimming streams, XDRIM. Streams can grow indefinitely, consuming memory. XDRIM allows you to manage the stream size. XDRIM key, maxlen tilde count. maxlen trims the stream to a maximum of count entries, an optional argument for fuzzy trimming. Instead of strictly trimming to count entries, Redis will trim to at least count entries, but might keep a few more for efficiency. This is often preferred in production to avoid continuous memory reallocations. 127.0.0.1:6379, XDRIM sensor data, maxlen 1000 hash, keep only the last 1000 entries. Integer, 357, hash number of entries removed. Reading from a stream. XREAD. XREAD is used to fetch entries from one or more streams. XREAD count, block milliseconds streams key, ID. Count, optionally specify the maximum number of entries to read. Block milliseconds makes the command a blocking read. If no new entries are available, the client blocks for milliseconds. 0 means block indefinitely. Streams key, ID. Specifies which streams to read from and from which ID to start reading for each stream. For the ID, 0 to 0 means start from the beginning of the stream. $sign means read only new messages added after this command, effectively reading from the most recent entry. This is common for continuous reading from the tail of a stream. Read all entries from the beginning of sensor data. 127.0.0.1:6379, XREAD streams sensor data 0 to 0. 1 sensor data. 2 1 1,700,678,400,000 to 0. 2 1 sensored. 2 1 3 temp. 4 24.5. 5 hum. 6 60.1. 2 1 1,700,678,400,000 to 1. 2 1 sensored. Block for 5 seconds and read up to 1 entry from sensor data, starting from the latest ID. 127.0.0.1:6379, XREAD block, 5000 count, 1 stream sensor data. If new data arrives within 5 seconds, it will be returned. Otherwise, after 5 seconds, an empty result is returned. Consumer groups, distributed and acknowledged processing. This is where streams truly differentiate themselves from lists for message queuing solutions. Consumer groups allow multiple independent clients, consumers, to collectively process the same stream. Redis keeps track of which messages each consumer in a group has processed. 1. Creating a consumer group. XGRUP create. XGRUP create key group name ID MK stream. Key, the name of the stream. Group name, the name of the consumer group you are creating. ID, the ID from which the consumer group should start reading messages. Common choices are 0 to 0, from the beginning of the stream, or from the latest entry. MKSDREAM, optional. If the stream key does not exist, it will be automatically created. 127.0.0.1:6379. XGRUP, create sensor data migroup 0 to 0 MKSDREAM. OK. Now, multiple consumers can join migroup to read from sensor data. 2. Reading from a consumer group, XRADGRUP. XRADGRUP group name consumer name, count, block milliseconds streams key, ID. Group name consumer name. Specifies the consumer group name, and the individual consumer instance within that group, consumer name. Streams key ID, the stream and the ID to read from. Greater than, this is the special ID used with consumer groups. It means read the next message that has not yet been delivered to any consumer in this group. It's the most common and recommended way to read from a group. Any specific ID can be used to read pending messages that were delivered to but not yet acknowledged by this consumer or another consumer in the group. Consumer 1 of migroup reads up to 10 new messages. 127.0.0.1:6379. XRADGROUP group. Migroup consumer 1 count 10 streams, sensor data Redis, will deliver a batch of messages to consumer 1, internally marking them as pending for consumer 1. These messages will not be delivered to other consumers in migroup until they are acknowledged or claimed. 3. Acknowledging messages, XACK. After a consumer successfully processes a message, it should acknowledge it back to Redis using XACK. This removes the message from the pending list for that consumer within the group. XACK key group name ID. 127.0.0.1:6379. XACK sensor data migroup 1,700,678,400,000 to 0. Integer 1#1 message acknowledged. 4. Exploring pending messages, XBNDNG. If a consumer crashes or fails to process a message, that message remains in its pending state. XBNDING helps you inspect these messages. XBNDING key group name, start and count, consumer name, returns a list of pending messages detailing their ID, consumer, time since pending, and number of deliveries. 5. Claiming messages from other consumers. XCLIM. If a consumer fails permanently, its pending messages need to be reprocessed. XCLAIM allows another consumer in the same group to take ownership of pending messages from a failing consumer. XCLAM key, group name, consumer name, min idle time, ID, force justed. Consumer name, the consumer that will claim the messages. Min idle time, messages must have been idle unacknowledged for at least this many milliseconds to be claimed. ID, the IDs of the messages to claim. This mechanism ensures reliable message delivery and processing by allowing for fault tolerance and recovery of failed operations. Practical use cases for Redis streams. Redis streams are incredibly powerful for scenarios that demand an ordered, durable log of events and reliable, distributed processing. A. Event sourcing and activity feeds. Every user action or system change can be an event added to a stream. This creates an immutable log of all that has happened, which can be replayed or analyzed. User activity feed. XADD user 123, activity type liked target posted 456. Consumers can read from this to display a user's activity. Audit logs. Every significant operation, e.g., user created, order placed, can be appended to an audit stream for later analysis or compliance. B. Durable message queues. Unlike lists where LPOP removes a message immediately, streams with consumer groups allow for explicit acknowledgement, making them suitable for ensuring every message is processed exactly once, even with multiple workers. Order processing. XADD order queue orderid 123 status new. Workers in an order processor's consumer group would XREADGROUP orders, process them, e.g., update database, send confirmation email, and XACK them. If a worker fails, its unacknowledged orders can be reclaimed by another. C. IoT data ingestion. Sensors in IoT devices generate continuous streams of data. Redis streams are an excellent ingest layer. XADD sensor. ID temperature 25.1, humidity 60.3, timestamp 1,700,678,400,000. Different consumer groups can then process this data. One group for real-time dashboards, another for historical archiving, a third for anomaly detection. D. Real-time activity feeds. Combining XADD with XREAD block allows for building real-time activity feeds, where new entries are pushed to connected clients as soon as they occur. Clients can read from the ID to get only new items. Streams versus lists versus PubSub for messaging. It's helpful to understand when to choose one for messaging solutions. Feature Redis lists as queue, Redis PubSub, Redis streams. Durability, yes, if persistence on, no fire and forget. Yes, if persistence on. Ordering FIFO, no guaranteed order, strict insertion order, by ID. Acknowledgement, no message is removed on POP, NA, yes, with consumer groups. Consumer groups not built in, must manage manually. Not applicable, yes, built in. Multiple readers, destructive read, one reader consumes. Non-destructive, all subscribers get it. Non-destructive, multiple readers. Groups. Complexity, low, moderate, due to consumer groups. Key use cases, simple work queues, stacks, real-time chat, notifications, event sourcing, durable queues, IoT. Audit logs. Redis streams represent a significant capability for modern, event-driven applications, providing durable messaging, distributed processing, and persistent logging, all within the high-performance Redis ecosystem. They are a powerful tool to have in your developer toolkit. In the next chapter, we'll shift our focus to even more specialized data types and functionalities, exploring hyperlog for approximate counting and geospatial functions for location-based services, further demonstrating Redis's versatility. Beyond the standard, hyperlog and geospatial functions, we've covered Redis's core data structures, strings, hashes, lists, sets, and sorted sets, and explored advanced features like transactions, pipelining, Lua scripting, and streams. Now, let's delve into two highly specialized, yet incredibly powerful, Redis functionalities that tackle very specific, common problems in application development. Approximate unique counting for massive datasets using hyperlog and location-based services with geospatial indexes. These features showcase Redis's versatility beyond being just a general-purpose data store, enabling efficient solutions to problems that would otherwise be computationally expensive or memory-intensive. Hyperlog, approximating unique counts. Imagine you need to count the number of unique visitors to your website daily, or the number of unique search queries, or the number of distinct items viewed by users. For small numbers, a Redis set, SADD and SCARD, works perfectly. However, what happens when you have hundreds of millions or billions of unique items? Storing all those distinct IDs in a set would consume enormous amounts of memory. This is the problem hyperlog HLL solves. It's a probabilistic data structure that provides an extremely efficient way to estimate the number of unique items in a large dataset with a very small, fixed amount of memory. How it works conceptually, without diving too deep into the complex algorithms, which involve hash functions and bit patterns, the core idea behind hyperlog is to count the occurrences of certain patterns in the hash values of the elements being added. Based on these patterns, it can statistically estimate the cardinality, number of unique elements of the set. The beauty is that the memory required to store the HLL structure is constant, typically around 12 KB, regardless of whether you're estimating the uniqueness of thousands or billions of items. Key commands: PFADD key element, probabilistic filter ADD. Adds one or more elements to the hyperlog probabilistic set represented by key. Returns 1 if the state of the hyperlog was changed, e.g., a new element was added that affected the estimation, 0 otherwise. 127.0.0.1:6379 PFADD Uniqua visitors. 2023 to 11 to 15 user, 101 user, 102 user, 103. Integer 1. 127.0.0.1:6379 PFADD unique visitors. 2023 to 11 to 15 user, 101 user, 104. Integer 1. PFCONT key, probabilistic filter count, returns the approximated cardinality, number of unique elements, of the hyperlog logs represented by keys. If multiple keys are provided, it returns the cardinality of the union of all HLLs. 127.0.0.1:6379 PFCOUNT unique visitors. 2023 to 11 to 15. Integer 4 hash estimated unique count of user 101, 102, 103, 104. PFMERG diskai Sorsky probabilistic filter merges multiple hyperlog source keys into a single diskai. The diskai will then represent the cardinality of the union of all merged HLLs. This is useful for combining daily unique counts into weekly or monthly totals. 127.0.0.1:6379 PFADD unique visitors 20,231,116 user, 105 user, 106. Integer 1. 127.0.0.1:6379 PFMERG unique visitors week 1 unique visitors. 2023 to 11 to 15 unique visitors 20,231,116. OK. 127.0.0.1:6379 PFCOUNT unique visitors week 1. Integer 6 hash estimates 101, 102, 103, 104, 105, 106 unique users. Precision and trade-offs. Hyperlog offers an impressive balance of memory usage and accuracy. The standard error for a single HLL data structure is typically around 0.81%. This means that for a count of 1 million unique items, the estimate will typically be within roughly 80/100 of the true value. For most analytical and reporting purposes, e.g., showing trends in website traffic, this level of accuracy is perfectly acceptable, especially given the massive memory savings. When to use hyperlog. When you need to count unique items in very large datasets, millions or billions. When a small margin of error, e.g., 0.81%, is acceptable for your use case. When memory efficiency is a critical concern. When not to use hyperlog, when you need a perfectly precise count, e.g., for financial transactions or inventory management. In such cases, use Redis sets if the dataset is manageable or a traditional database. When you need to retrieve the actual unique items, not just their count. Geospatial functions. Location-based data. Modern applications frequently deal with location data. Finding points of interest near a user, building ride-sharing services, or defining geographical boundaries. Redis's geospatial indexing capabilities make these tasks remarkably efficient. Redis's geospatial commands allow you to store pairs of latitude-longitude coordinates, assign a name to each location, and then query them based on their distance from a given point or within a specific radius. How it works conceptually. Redis uses a geohash as the underlying data structure, which maps 2D coordinates, latitude and longitude, into a single 1D string. This string can then be stored in a sorted set, where the score is a value derived from the geohash. This allows Redis to leverage the efficient range queries of sorted sets to find nearby locations. Key commands. All commands assume a specified unit for distances: m, meters, km, kilometers, ft, feet, mi, miles. GEOADD key longitude latitude member longitude 2 latitude 2 member 2. Adds one or more geospatial items, members, with their longitude and latitude coordinates to the specified key. The member can be any string. Longitude must be between -180 and 180, and latitude between -85.0, 5112878 and 85.05, 112.878. 127.0.0.1:6379 GEOADD cafes 13.361389 38.115556. Palermo Cafe 15.087268337.502669, Catania Espresso. Integer 2, GEOPOS key member, geospatial position, returns the longitude and latitude coordinates of the specified members from the geospatial index stored at key 127.0.0.1:6379, GEOPOS cafes, Palermo Cafe. 1 13.361389338970 2 38.11555639563046 Geodist key member 1 member unit, geospatial distance, returns the distance between member 1 and member 2 in the specified unit. 127.0.0.1:6379 GEODIST cafes, Palermo Cafe, Catania Espresso, KM. 166.2742, hash approx 166 km apart. GEORDAS key longitude latitude radius unit with coord, with dist, with hash, count ask desk, store key, storedist key. Returns members within a certain radius from a given longitude and latitude point. WITHCORD returns coordinates along with members. WITHDIST returns distance from the center along with members. WITHHASH returns the 52-bit geohash integer. Count limits the number of results. Ask desk orders the results by distance, ascending or descending. Store key / SDOREDIST key stores the results or results with distances into a sorted set which can then be returned. Find cafes within 200 km of a central point, e.g. Siracusa coords 127.0.0.1:6379, GEORDUS cafes, 15.286915537.0, 75416 km, WITHDIST, WITHCORD. 1 Catania Espresso. 2 23.9575. 3 15.087267923355103. 2 37.50 26689849567. 2 Palermo Cafe. 2 166.2741. 3 13.361389338970 2 38.11555639563046. GEORDAS BYMEMBR key member radius unit with coord, with dist, with hash, count ask desk, store key, storedist key. Similar to GEORDAS, but instead of defining a central point by coordinates, it uses an existing member in the geospatial index as the center. Find other cafes within 150 km of Catania Espresso. 127.0.0.1:6379 GEORDAS BYMEMBR cafes, Catania Espresso. 150 km WITHDST. 1 Catania Espresso. 2 0.0000. 2 Palermo Cafe hash will be outside 150 km range from previous example, 166 km away. 2 166.2742. GEOHASH key member returns the geohash string for one or more members. 127.0.0.1:6379 GEOHASH cafes, Palermo Cafe. 1 SQC 8B2S16. Practical use cases for geospatial functions. A. Finding nearby places. This is the most common use case. Restaurants shops near me. Given a user's location, find all restaurants within a 5 km radius. Service providers. Locate the nearest plumber, electrician, or doctor. Conceptual application. Add users' office locations. Redis GeoAdd. Offices, -74.0060, 40.7128, NYC office, hash New York. Redis GeoAdd. Offices, 0.1278, 51.5074, London office, hash London. User wants to find the nearest office. Application provides userlong. Userlat. The application would then query like GEORDAS offices, userlong userlat 50 km, WITHDIST, WITHCORD. And display results. B. Ride-sharing and delivery services. Optimizing pickup and delivery. Finding nearby drivers. When a user requests a ride, query for active drivers within a certain radius. Delivery zones, checking if a delivery address falls within a service area. See real-time location tracking. While not primarily designed for continuous, high-frequency tracking, streams might be better for that. Geospatial indexes can quickly answer, where is object X now? Or, which objects are in this region? Event venue discovery. Finding events happening near a user. Venues could be stored with GEOADD, and users can query for events happening around their current location. Summary: Hyperlog and Redis geospatial functions are excellent examples of Redis's ability to offer highly optimized solutions for specific, complex data problems. Hyperlog tackles the challenge of unique counting at scale with impressive memory efficiency and acceptable accuracy. Geospatial functions provide a simple yet powerful way to store and query location data, enabling a wide range of location-aware features in your applications. By understanding these specialized data types, you can choose the right tool for the job, leveraging Redis's speed and versatility to solve diverse challenges in modern application development. In the next chapter, we'll turn our attention to common architectural patterns, showing how the various Redis data structures and features come together to implement crucial components like caching, session management, and robust counters, tying theory directly to practical application. Common developer patterns: caching, session management, and counters. We've covered Redis's diverse data structures and advanced features in detail. Now, it's time to put that knowledge into practice. This chapter focuses on how developers leverage Redis to implement fundamental architectural patterns that address common challenges in modern applications. Improving performance with caching, handling user state with session management, and tracking metrics with various counter types. These patterns are critical for building scalable, responsive, and robust systems that can handle high traffic and provide a seamless user experience. Caching strategies with Redis. Problem: database queries are often slow, network calls to external services are latency-prone, and computed results can be expensive to generate. Repeatedly fetching or computing the same data for every request burdens backend systems and increases response times. Solution: caching. By storing frequently accessed or computationally intensive results in a fast, in-memory store like Redis, applications can serve requests much quicker, reduce load on primary data sources, and improve overall throughput. Redis, with its speed, versatile data structures, especially strings and hashes, and built-in expiration mechanisms, is an ideal caching layer. Popular caching patterns: cache-aside lazy loading. This is the most common and often recommended caching pattern. How it works: when an application needs data, it first checks Redis. Cache hit: if found, the data is returned immediately. Cache miss: if not found, the application fetches the data from the primary data source, e.g., database, stores it in Redis, often with a time to live TTL, and then returns it to the client. Pros: simple to implement. Only retrieves and caches data that is actually requested, avoiding caching unused data. Cons: cache misses can lead to a slight delay as data must be fetched from the primary source. Stale data can exist if the primary source is updated but the cache entry hasn't expired yet or isn't explicitly invalidated. Redis implementation: data type, strings or hashes for structured objects. Commands: get SETEX for strings with TTL, HGTALL, HSET for hashes with expire on the hash key. Conceptual code example: Python-like pseudocode, def get product producted, hash1. Try to get from Redis. ProductISN equals Redis client get, f product, producted. If productISN, print, cache hit. Return JSON loads, productISN. Hash2, if cache miss, fetch from database. Print, cache miss. Fetching from DB. Product data equals DB fetch productBid, producted. If product data, hash3. Store in Redis with an expiration, e.g., 5 minutes. Redis client setx, f product, producted. 300 JSON dumps product data. Return product data. Return none. Write through. How it works: data is written simultaneously to both the cache and the primary data source. The application waits for both writes to complete. Subsequent reads go directly to the cache. Pros: data in the cache is always fresh. Read operations are always fast. Cons: write operations are slower because they involve two steps. Potential for complexity if one write fails. Redis implementation: less common as the primary write pattern for Redis, but can be simulated. Typically, the application would perform an HSET or set, and then also update the database in the same logical operation, though perhaps not in a single atomic transaction. Write back, write behind. How it works: data is written only to the cache first, and the application receives an immediate acknowledgement. The cache then asynchronously writes the data to the primary data source. Pros: very fast write operations. Cons: risk of data loss if the cache server crashes before data is persisted to the primary source. More complex to implement due to asynchronous nature. Not recommended without strong persistence guarantees or in scenarios where data loss is unacceptable. Redis implementation could involve RPUSHing a message to a list after caching the data, with a separate worker consuming the list and writing to the database. Cache eviction and invalidation, TTL, time to live, the most straightforward way to manage cache freshness. Data simply expires after a set duration expire, SETEX. LRU, least recently used, and LFU, least frequently used. Redis supports these eviction policies. When Redis reaches its max memory limit, it will automatically remove keys based on these algorithms, max memory policy in redis.conf. This is useful for volatile caches. Explicit invalidation. When data in the primary database changes, you can explicitly del the corresponding keys from Redis to ensure consistency. This can be triggered by database triggers, application logic, or pub/sub pattern, as discussed in Chapter 8. Developer tip: for structured data, like product details, hashes are often more efficient than storing the entire object as a JSON string, as you can update individual fields, HSET, without reserializing the whole object. User session management. Problem: web applications need to maintain user state across multiple requests. In distributed environments, e.g., microservices, load-balanced servers, simply relying on server-side memory for sessions is problematic because a user's subsequent request might hit a different server. Solution: store session data in an external, shared, fast key-value store. Redis is an excellent choice. How it works: when a user logs in, the application generates a unique session ID. Session-specific data, e.g., userid, roles, carded, is stored in Redis, keyed by the session ID. The session ID is then sent to the client, e.g., as a cookie or JWT payload. On subsequent requests, the application retrieves the session ID from the client, uses it to fetch the latest session data from Redis, and processes the request. Redis's expire command is used to automatically invalidate sessions after a period of inactivity. Redis implementation: data type, hashes for structured session data or strings for simple session tokens IDS. Commands: HSET, HGETALL, expire, TTL, del. Conceptual code example: Node.js/express like pseudocode. Const express equals require express. Const app equals express. Const UUID equals require UUID. Const Redis equals require Redis, create client, middleware to manage session. App.use, async rec raise next equals. Let sessionid equals rec.cookies sessionid. Let session data equals. If sessionid, try to load existing session. Session data equals await Redis h get all, f session, session ID. If session data object keys, session data. Length equals 0. Session expired or not found, create new. Sessionid equals UUID v4. Session data equals, clear any loaded stale data. Else, session found, refresh expiration time, keep alive. Await Redis expire, f session, session ID, 1800. 30 minutes. Else, no session ID, create a new one. Sessionid equals UUID v4. Rec session equals session data. Make session data available. Rec session ID equals sessionid. Make session ID available. Raise.cookie sessionid, HTTP only, true max age, 1,800,000, 30 mins. Next, example route for login. App post/login, async rec raise equals. Validate user credentials. If user authenticated, rec.session.userid equals userid. Rec.session.username user.username. Rec session logged in equals true. Save updated session data to Redis. Await Redis hset, f session rec session id, rec session, res send, logged in. Else, res status 401, send invalid credentials. This pattern offloads session storage from application servers, significantly simplifying horizontal scaling and making servers stateless. Counters. Tracking metrics and beyond. Problem: applications frequently need to track numerical metrics. Website page views, likes on a post, remaining stock for a product, API call limits, or unique object identifiers. These counters must be updated concurrently and atomically. Solution: Redis provides native atomic increment decrement operations on strings and hash fields, making it perfect for rapid, high-volume counter updates. Types of counters: simple global counters. Purpose: track a total count globally, e.g., total users signed up, total orders processed. Redis type: string. Commands: incr, incrby, decr, decrby. Example: redis.incr, app total users. Redis.incrby, app total traffic bytes, new request size 9 bytes. These are highly efficient and safe for concurrent updates from many application instances. Per object or per user counters. Purpose: track metrics associated with specific entities, e.g., likes on a product, views for an article, users' notification count. Redis type: hashes, often with the object ID as the hash key and the specific counter name as the field. Commands: hincrby, hincrbyfloat. Example: hash when userid 123 likes, fodoid 456. Redis hinkaby ffod 456 metrics, likes 1. Hash when fodoid 456 is viewed. Redis hinkaby ffod 456 metrics, views 1. This keeps all metrics for a single object grouped together and allows atomic updates of individual metrics. Unique counters approximated. Purpose: count a large number of unique occurrences, e.g., unique visitors to a website. Redis type: hyperlog log covered in Chapter 11. Commands: pfadd, pfcount. Example: hash user 101 visits homepage. Redis fad, homepage unique visitors 2023 to 11 to 20. User 101. Hash later get the unique count. Redis pf count, homepage unique visitors 2023 to 11 to 20. Provides excellent memory efficiency for large approximate unique counts. Counters with expiration event horizon. Purpose: counters that should reset or become irrelevant after a certain period, e.g., today's views, rate limiting counters for a 60-second window. Redis type: strings or hashes combined with expire. Commands: incr, hincrby, expire, setx. Example: daily counter. Hash get today's date for the key. Tadiki equals data time now. strf time, %y, %m, %d. Total viewski equals f daily views tadiki. Hash increment, and set refresh expiry to 24 hours from now. Current views equals redis client.incr, total viewski. Hash only set if it's a new key this day, or if you want to extend the expiry with every read. If current views equals 1, hash this helps only set expire once per day for high traffic. Redis client expire, total views key, 24*3600. For more complex rate limiting with sliding windows, Redis Lua Scripting, Chapter 9, is often employed. Summary: these three patterns, caching, session management, and various types of counters, are foundational to building modern, high-performance web applications. Redis's speed and specialized data structures provide powerful and often simpler alternatives to traditional database solutions for these specific problems. By correctly applying these patterns, developers can offload significant work from their primary databases, reduce latency, and scale their applications more effectively. In the next chapter, we'll continue exploring practical applications of Redis by looking at how it can be used to build reliable systems, focusing on distributed locks, advanced job queues, and more sophisticated rate limiters. Building reliable systems, locks, queues, and rate limiters. In distributed systems, where multiple application instances or services operate concurrently, ensuring data consistency, proper resource access, and fair usage becomes complex. Redis, with its atomic operations and powerful data structures, provides elegant solutions for commonly encountered distributed system challenges. This chapter delves into how Redis can be leveraged to build robust distributed locks, flexible job queues, and sophisticated rate limiters. Distributed locks, coordinating concurrent operations. Problem: in a distributed environment, multiple processes or threads might try to access and modify the same shared resource, e.g., updating a database record, processing a unique job, or performing a critical section of code. Without proper coordination, this can lead to race conditions, data corruption, or inefficient use of resources. Traditional mutexes or semaphores only work within a single process or machine. Solution: a distributed lock allows one and only one client at a time to hold a lock for a given resource across multiple processes or machines. Redis is a popular choice for implementing distributed locks due to its speed, atomic commands, and built-in expiration, TTL. Basic distributed lock using Redis. The most straightforward way to implement a distributed lock uses the setnx command, set if not exists, combined with an expiration. Acquiring the lock. A client attempts to acquire a lock by executing setnx lockkey unique value. If setnx returns 1, the client successfully acquired the lock. If setnx returns 0, another client already holds the lock. Setting an expiration. Immediately after acquiring the lock, the client must set a TTL on lockkey using expire lockkey timeout in seconds. This is crucial to prevent deadlocks if the client that acquired the lock crashes before releasing it. Crucial improvement. The set command in modern Redis versions, 2.6.12+, offers atomic setnx and expire functionality. Set lockkey unique value nxpx timeout in millisecons. This command will set the key only if it doesn't exist, nx, and concurrently set its expiration, px for milliseconds, ensuring the lock always has a timeout. Releasing the lock. The client releases the lock by deleting lockkey using del lockkey. This should only be done if the unique value matches what the client set, preventing a client from accidentally releasing a lock acquired by another client, especially if TTL expired and another client reacquired it. A Lua script is often used for safe release. Conceptual Python-like pseudocode, atomic set for acquisition, Lua for safe release, def acquire lock, lock name, acquire timeout equals 10, lock timeout equals 5. Identifier equals, unique wait for this lock attempt. Lock key equals f lock lock name. End time equals time, plus acquire timeout. While time, end time, hash try to set the key if it doesn't exist with an expiration. Hash returns true if set, false otherwise. If Redis client set, lockkey identifier nx equals true, px equals lock timeout 1000. Return identifier hash lock acquired. Time sleep 0.01. Hash wait a bit before retraying. Return none hash failed to acquire lock within timeout. Def release lock, lock name identifier. Lockkey equals f lock lock name. Hash use a Lua script to atomically check value and delete. Hash this prevents deleting a lock that has expired and been reacquired by someone else. Lua script equals, if redis.call, get, keys1 equals argv1 then. Return redis.call, del keys1, else, return 0, and return redis client eval, Lua script 1 lockkey. Identifier equals 1. Important considerations for distributed locks. Deadlock prevention, always set an expiration TTL on locks. Safety correctness, ensure a client only deletes locks it owns. Using a unique value identifier and checking it before del, preferably with a Lua script, is crucial. Liveness availability, what if the service holding the lock crashes before releasing it? The TTL helps, but if the TTL is too short, the lock might expire prematurely. If it's too long, recovery from a crash is delayed. Redlock. For extremely high-assurance distributed systems, e.g., controlling expensive hardware or critical bank transactions, a more complex algorithm called redlock was proposed by the Redis creator. Redlock involves attempting to acquire locks on a majority of independent Redis instances to improve robustness against single-point failures and clock drifts. While more resilient, Redlock is also more complex to implement and manage, and its necessity and guarantees are a subject of ongoing debate in the distributed systems community. For most applications, a single Redis instance with SETNX expire and careful client-side retry logic is usually sufficient. Job queues, asynchronous task processing. Problem: many operations in modern applications, e.g., sending emails, processing images, generating reports, don't need to be completed instantly as part of a user's request. Performing them synchronously can slow down the user experience or overload the server. Solution: asynchronous job queues. A producer, e.g., web server, adds a job to a queue, and a separate worker process picks up and processes the job at its own pace. Redis is widely used for this due to its list and stream data types and blocking operations. 1. Simple queues with lists, basic FIFO. Producer uses LPUSH or RPUSH to add jobs. Consumer uses LPOP or RPOP to retrieve jobs. For blocking behavior, use BLPOP or BRPOP. Conceptual BLPOP usage. Producer, Redis client rpush, email queue, send welcome email, user 123. Worker, while true, hash block until a job is available or for 60 seconds. Job data list equals Redis client BLPOP, email queue, timeout equals 60. If job data list, queue name, job payload equals job data list. Printf processing job, job payload. Hash, process job, trade-offs, simple, fast. Lack of built-in acknowledgement mechanisms or consumer groups. If a worker crashes after popping a job, but before fully processing it, the job is lost. 2 reliable queues with RPOPLPUSH. To address job loss for simple list queues, RPOPLPUSH can be used to move a job from a pending queue to an in progress queue atomically. Producer, RPUSH job queue job details. Worker, atomically get and move job. Job data equals Redis client rpush. Job queue, in progress queue. Process job data, if successful. Redis client LREM, in progress queue, 1 job data, removes job from in progress queue. Recovery, if worker crashes, jobs remain in progress queue. A separate monitor can periodically scan in progress queue for jobs older than a threshold and move them back to job queue using LREM and RPUSH or a dead letter queue. Conceptual RPOPLPUSH usage, worker code. While true, job payload equals Redis client rpush. MyJobs processing. If job payload, try, process job payload. Redis client LREM, MyJobs processing, 1 job payload hash remove after success. Accept exception as E. Printf error processing job payload, E. Hash job remains in MyJobs processing, recovery mechanism needed. Else, hash no jobs, maybe sleep or wait if not blocking. Time sleep 1. 3. Advanced queues with streams, durable, consumer groups, acknowledgement. As discussed in Chapter 10, Redis streams with consumer groups offer a robust and feature-rich solution for durable messaging and job queues. They address the limitations of lists by providing explicit acknowledgement. XACK confirms successful processing. Consumer groups. Multiple workers can efficiently consume from the same stream, with Redis managing message distribution and pending state. Persistence. Messages are not lost on worker crashes or Redis restarts. Visibility timeout. Messages remain in the pending list until acknowledged, allowing for recovery. Example workflow using streams. XADD misstream job data. Producer adds job. XGRUP, create misstream migroup 0 to 0 MKSTRAM. Create group once. XRADGROUP group, migroup worker id, count 1 SDRAMS misstream. Worker reads next available job. XACK misstream migroup jobid, worker acknowledges job. XBNDING, and XCLAIM for recovery management. Streams are generally the preferred method for building modern, resilient job queues with Redis. Rate limiters, protecting resources. Problem: APIs and services can be overwhelmed by excessive requests from individual clients, leading to denial of service, DoS, or unfair resource usage. Solution: rate limiting restricts the number of requests a client can make within a specified time window. Redis's speed and atomic operations are perfectly suited for this. 1. Fixed window counter, simple but flawed. How it works: maintain a counter for each client within a fixed time window, e.g., 60 seconds. Redis type: string for the counter. Commands: incr expire. Conceptual logic: def checkfix rate limit, cliented limit equals 100, windowscons equals 60. Key equals f rate limit, fixed cliented. Current count equals Redis client.incr, key, hash atomically increment counter. If current count equals 1, Redis client expire, key, windowscons, hash set expiration if new window. If current count limit, return false hash rate limit exceeded. Return true hash request allowed. Flaw: the edge case problem. A client could make limit requests at the very end of one window and limit requests at the very beginning of the next, effectively making two limit requests in a short period around the window boundary. 2. Sliding window log, more accurate, memory intensive. How it works: store a timestamp for each request within a sorted set or list. On each request, remove timestamps older than the window, then add the new timestamp and check the count. Redis type: sorted set with timestamps as scores. Commands: zadd, zrmrngbyscre, zcard. Conceptual logic: this pattern is best implemented using a Redis Lua script, as demonstrated in Chapter 9, Atomic Rate Limiter, Sliding Window Log. The script ensures atomicity and efficiency by combining multiple Redis operations into a single server-side call. Benefits: highly accurate, provides true sliding window. Drawbacks: can be memory intensive if many requests are stored for many users in long windows. Each request is an entry in the sorted set. 3. Token bucket, most granular and flexible. How it works: imagine a bucket of tokens. Requests consume tokens. Tokens are added to the bucket at a fixed rate up to a maximum capacity. If a request arrives and there are no tokens, it's denied. Redis type: hash to store tokens and last update timestamp for each client. Commands: hget, hset, but the logic is usually implemented with a Lua script for atomicity and calculation. Conceptual logic simplified. Calculated token stowed equals now last fill time, refill rate. Current tokens equals min, bucket capacity, last tokens plus calculate token stowed. If current tokens equals 1, then current tokens equals current tokens 1. Redis hset. Return success. Benefits: flexible bursting allowed up to bucket capacity, smoothizes traffic. Drawbacks: more complex to implement, requires careful Lua scripting. Choosing the right rate limiting strategy depends on the precision required, memory constraints, and tolerance for complexity. For most cases, a well-implemented sliding window log using Lua scripts is a good balance. Summary: Redis is not just a high-performance data store. It's a powerful toolkit for building reliable and scalable distributed systems. Its atomic operations, flexible data structures, and scripting capabilities enable robust solutions for distributed locks, ensuring mutual exclusion across services, leveraging set NXPX and Lua scripts. Job queues, implementing asynchronous processing patterns, using lists for simplicity or streams for durability and consumer group features. Rate limiting, protecting your APIs and resources with fixed window, sliding window, or token bucket algorithms, often powered by Lua scripting. Mastering these patterns is crucial for any developer working on distributed applications. In the next chapter, we'll explore how Redis's functionality can be enhanced even further through Redis modules, opening up new possibilities like full-text search and graph databases directly within Redis. Redis modules in action, enhancing capabilities. Throughout this book, we've explored Redis's core data structures and its inherent capabilities for caching, session management, messaging, and building reliable systems. Yet, one of Redis's most powerful architectural features is its extensibility through Redis modules. Introduced in Redis 4.0, modules allow developers to extend Redis's functionality natively, adding new data types, commands, and functionalities that operate with the same performance and atomicity as Redis's built-in commands. What are Redis modules? Redis modules are dynamic libraries written in C or other languages that can compile to C ABIs that can be loaded into the Redis server at startup or runtime. They get direct access to Redis's internal data structures and APIs, letting them integrate seamlessly. This means a module can, Introduce new data types, like a JSON document store or a time series database. Add new commands. For example, a search index module could introduce FT search for full-text queries. Implement new functionalities, such as graph capabilities or machine learning inference. The key advantage is that these extensions operate with Redis's speed and concurrency guarantees, as they run within the same event loop and adhere to its single-threaded model for data access. Though Redis itself uses threads for I/O and other background tasks, they feel like native Redis commands. Why use Redis modules? Performance. Commands implemented in modules run directly on the server, minimizing network latency compared to complex multi-command operations from clients. Atomicity. Operations within a module command are atomic, just like built-in Redis commands, ensuring data consistency. Encapsulation. Complex logic can be encapsulated within a module, simplifying client-side code and reducing the burden on application developers. Specialization. Modules enable Redis to act as a multi-model database, providing highly optimized solutions for specific data models, e.g., documents, graphs, time series, without needing separate dedicated databases. Ecosystem expansion. They foster a vibrant ecosystem of specialized functionalities for Redis. How to use Redis modules conceptually. To use a Redis module, you typically need to obtain the module, download the SO Linux Mac OS or DLL Windows file for the module, load the module, configure your redis.conf file to load the module at startup, load module path /to/mymodule.so, or load it at runtime, though not recommended for production setups as it's not persistent across restarts. Module load path /to/mymodule.so. Use new commands. Once loaded, the new commands introduced by the module become available in Redis CLI and through Redis client libraries. Popular Redis modules. The Redis community has developed a rich set of modules. Let's look at some of the most impactful ones. 1. Redis Search. Full-text search and secondary indexing. Problem: Redis's core data types aren't designed for full-text search, e.g., finding documents containing specific words, performing fuzzy matches, or ranking relevance. Doing this manually with sets or sorted sets is cumbersome and inefficient. Redis Search Solution. Redis Search transforms Redis into a high-performance search engine. It allows you to index documents, create complex schema definitions for your data text fields, numeric, tag, geo, perform full-text queries, supports logical operators and, or not, phrase matching, prefix matching, fuzzy matching, and more. Filter and aggregate. Combine text searches with numeric, tag, and geospatial filters. Sort and paginate results. Core commands conceptual. FT create mindex schema title text body text price numeric tags tag. FTADD mindex doc 1.1.0 fields title Redis book. Body. This is a book about Redis. Price 29.99 tags programming. Database. FT search mindex Redis book. SORTBY price desk return to title price. FT aggregate mindex at price 0.50. GROUPBY at tags reduce count 1. Use cases. E-commerce product search, site search, real-time article indexing, filtering activity feeds. 2. Redis JSON document store. Problem: while you can store JSON as a plain string, managing and updating parts of a JSON document, getting, parsing, modifying, and setting back, is inefficient and prone to race conditions if not handled carefully with transactions or Lua. Redis JSON solution. Redis JSON introduces a native JSON data type. It allows you to store and manipulate JSON, set and retrieve JSON documents directly, update specific paths, read, write, and delete nested values within a JSON document using JSON path-like syntax, atomically. Search JSON documents, often used in conjunction with Redis Search to index and query JSON documents. Core commands conceptual. JSON set user 1 name, Alice, address, city, New York, zip, 10,001. JSON get user 1 address $city. JSON set user 1 address $zip, 10,002. JSON.del user 1 address $zip. Use cases. User profiles, product configurations, content management, any application that heavily uses JSON documents. 3. Redis graph database. Problem: representing and querying highly interconnected data, like social networks, recommendation engines, or dependency maps, is complex and inefficient with traditional relational databases or even general-purpose NoSQL stores. Redis graph solution. Redis graph turns Redis into a fast, in-memory graph database, powered by a compact graph representation called GraphBLAS and supporting a subset of the Cypher query language. It allows you to store nodes and relationships, define entities, nodes, and their connections, relationships with properties, perform graph traversals, execute complex graph queries efficiently. Core commands: conceptual. Graph query social: create, person name, Alice, person name, Bob, a person name, Charlie. Graph query social: match a person name, Alice, B person name, Bob, create A, follows B. Graph query social: match P, person, follows F, person where P.name equals Alice, return F.name. Graph query social: match P1, person, follows P2, person, follows P3, person, return P1.name, P3.name. Use cases: social networking, friend recommendations, fraud detection, network topology mapping, supply chain optimization. 4. Redis time series data store. Problem: storing and querying high-volume, time-ordered data, like sensor readings, stock prices, or application metrics, efficiently is challenging. Most databases struggle with the sheer write rate and specialized aggregations needed. Redis time series solution. Redis time series is a purpose-built time series database for Redis. It offers high ingest rates, optimized for ingesting millions of data points per second, automatic downsampling, aggregate data into lower resolutions, e.g., 1 second data to 1 minute averages. Range queries and aggregations. Query data for specific time ranges and perform aggregations: sum, average, min, max, count. Retention policies. Automatically prune old data to manage memory. Core commands: conceptual. TS-create sensor temperature retention, 604,800, hash 1 week retention. TS-add sensor temperature, 25.5 labels, sensorid 1 room kitchen. TS-add sensor temperature, 24.9, labels, sensorid 1 room kitchen. TS-range sensor temperature, 1,678,880, 6,401, 1,678,880, 7,400 aggregation. AVG 60, hash average per minute. Use cases: IoT sensor data, financial market data, application performance monitoring, APM, real-time analytics. Other notable modules. Redis Bloom implements probabilistic data structures like Bloom filters for checking set membership without storing all elements, and Cuckoo filters. Redis AI enables running machine learning inference directly within Redis, e.g., for real-time recommendations or fraud scoring. Redis Gears provides a programmable data processing engine for Redis, allowing you to run event-driven functions, like serverless functions, directly on Redis data, written in Python or C. Considerations when using modules. Ecosystem maturity. Modules can vary in maturity and feature completeness. Check their documentation and community support. Redis version compatibility. Ensure the module is compatible with your Redis server version. Deployment. Modules add external dependencies to your Redis deployment. You'll need to ensure the SO files are available and correctly loaded. Resource usage. While highly optimized, modules consume resources, memory, CPU. Monitor their impact on your Redis instance. Data model decisions. Using a module for a specialized data model means committing to that model. Ensure it aligns with your application's long-term needs. Redis modules empower Redis to transcend its traditional key-value store roots and become a formidable multi-model database. By leveraging these extensions, developers can simplify their architectures, improve performance, and address specialized data challenges directly within their familiar Redis environment. This capability significantly broadens Redis's applicability across many domains. In the next chapter, we will shift our focus to the operational aspects of Redis. exploring how to ensure data durability and recovery through various persistent strategies. Durability and recovery, persistent strategies. Throughout this book, we've emphasized Redis's incredible speed, largely attributed to its in-memory nature. However, unpersisted in-memory data is volatile. If your Redis server crashes or restarts, all your data would be lost. For many real-world applications, losing data is unacceptable. This is where Redis persistence comes into play. Redis provides robust mechanisms to save your in-memory dataset to disk, ensuring data durability and enabling recovery after a server restart or failure. Understanding these persistence options and their trade-offs is crucial for building robust Redis deployments. Redis offers two primary persistence mechanisms: RDB, Redis database, snapshotting, point-in-time snapshots of your dataset; AOF, append-only file, a durable log of all write operations. You can use either RDB, AOF, or a combination of both to achieve your desired level of data durability. 1. RDB persistence. Point-in-time snapshots. RDB persistence performs periodic snapshots of your Redis dataset. This means Redis saves the entire dataset at a specific moment to a binary file, default name dumprdb. How it works. When an RDB save is triggered, Redis forks a child process. The child process then writes the entire dataset to a temporary RDB file. Once the writing is complete, the old RDB file, if any, is replaced with the new one. This copy-on-write mechanism ensures that Redis can continue serving requests while the snapshot is being created, minimizing impact on performance. Configuration, redis.conf. The save directive in redis.conf defines the conditions for taking a snapshot. Save 901 hash save if at least one key changed within 900 seconds, 15 minutes. Save 310 hash save if at least 10 keys changed within 300 seconds, 5 minutes. Save 6010,000 hash save if at least 10,000 keys changed within 60 seconds, 1 minute. You can specify multiple save rules. If none are specified, or if you explicitly set save, RDB persistence is disabled. Other important RDB configurations: DB filename dumprdb, the name of the RDB file; dir, the directory where the RDB file will be saved. Stop writes on BG save error yes. If set to yes, Redis will stop accepting write commands if a BGSAVE, background save, fails, preventing data inconsistency. RDB compression yes. Uses LZF compression for RDB files, reducing disk space at the cost of some CPU. RDB checksum yes. Adds a checksum to the end of the RDB file to detect corruption. Manual saving, save and BGSAV. Save performs a synchronous save. The Redis server will be blocked during the entire save process. This should only be used rarely or for testing because it makes Redis unresponsive. BGSAV performs a background save. Redis forks a child process, which handles the saving. The main Redis process remains unblocked and continues serving requests. This is the preferred method for manual snapshots. Advantages of RDB. Compact single file. RDB files are compact, highly optimized binary representations of your dataset, making them good for backups and fast recovery. Fast restores. Restoring an RDB file is typically much faster than replaying an AOF log, especially for large datasets. Performance. The parent Redis process does no I/O during a BGSAVE, meaning it retains high performance. Disaster recovery. A single, self-contained RDB file can be easily transferred to remote data centers for disaster recovery. Disadvantages of RDB. Data loss risk. Since snapshots are taken periodically, if Redis crashes between saves, you will lose all data added or changed since the last snapshot. Forking cost. Forking can be expensive if your dataset is very large, potentially causing a brief latency spike as memory is duplicated, though Redis uses copy-on-write, so only changed pages are duplicated. Complexity with upgrades. RDB format can change between Redis versions, making it sometimes tricky to restore older RDB files with newer Redis versions, though Redis tries to maintain backward compatibility. 2. AOF persistence, append-only file. AOF persistence logs every write operation received by the Redis server. Instead of saving the entire dataset periodically, Redis appends each write command, set, lpush, incr, etc., to a chronological append-only file, default name append_in_layoff. When Redis restarts, it rebuilds the dataset by replaying all commands in the AOF file. How it works: Redis writes commands to the AOF in a format that's easy to replay. To avoid the AOF file growing indefinitely large, Redis supports AOF rewriting. This process creates a new, optimized AOF file that contains the minimal set of commands needed to reconstruct the current dataset. For example, if you incr a counter 100 times, the AOF will have 100 incr commands. AOF rewrite will turn this into a single set command on the final value. Configuration, redis.conf. Append_in_layoff yes enables AOF persistence. Append file name append_in_layoff, the name of the AOF file. Dir, the directory for the AOF file. AOF fsync policy, how often data is written from OS buffers to disk. Append sync always, every time a command is written to the AOF. Slow, very high I/O, but guarantees no data loss, most durable. Append sync eversec, fsync the AOF every second. Default and recommended. A good balance of durability and performance. You might lose up to 1 second of data in a crash. Append sync no, let the OS flush data when it wants. Fastest, but most data loss risk, could lose several seconds of data. AOF rewriting configuration. Auto AOF rewrite percentage 100. Triggers AOF rewrite when the AOF file size exceeds the auto AOF rewrite min size by this percentage. Auto AOF rewrite min size 64 MB. Minimum size AOF must reach for rewrite to be considered. Manual configuration. BGREWRITOF. BGREWRITOF triggers a background AOF rewrite. Like BGSAVE, this uses a child process to minimize impact on the main Redis process. Advantages of AOF: higher durability. Configurable fsync policy means you can achieve very high levels of data durability, e.g., losing only 1 second of data or even less. No data loss on crash. If AOF is enabled with append sync always, you are guaranteed not to lose any writes on crash. Audit trail. The AOF file is a human-readable log of all write operations. You can inspect it, though it's not designed for that. Disadvantages of AOF: larger file size. AOF files are generally larger than RDB files for the same dataset, especially before a rewrite. Slower restores. Replaying a large AOF file can take significantly longer to restore the dataset compared to loading an RDB snapshot. Performance impact. Even eversec can have a small performance impact compared to RDB, as Redis is constantly appending to the file. Rewrite complexity. AOF rewrite is a process that involves a fork, which can still incur a brief latency spike for very large memory footprints. Choosing a persistent strategy or combining them. The best strategy depends on your application's durability requirements and performance tolerance. No persistence. Use when Redis is used purely as a cache where data can be easily regenerated from a primary source, or for very transient data, e.g., real-time leaderboards that reset daily. Pros: maximum performance. Cons: all data lost on restart crash. RDB only. Use when you can tolerate some data loss, e.g., a few minutes of changes, but want fast restarts and compact backups. Typical for caching with higher durability needs or for read-heavy workloads where data can be partially regenerated. Pros: good performance, fast restores, compact files. Cons: potential for data loss. AOF only with eversec. Use when you need higher durability and can tolerate slightly slower restores and larger file sizes. Suitable for primary data storage where a second or two of data loss is acceptable. Pros: better durability than RDB, commands logged in human-readable format. Cons: larger files, slower restores than RDB. RDB plus AOF, recommended for high durability. Use when you need maximum data durability with quick and efficient recovery. This is the most common and recommended setup for production-critical applications. How it works. AOF provides the highest level of durability, losing at most 1 second of data with eversec. RDB snapshots can be used for initial, Faster reloads, e.g., on a full server restart, load the RDB, then apply any missing AOF changes since the RDB was taken. Pros: best of both worlds. High durability from AOF, fast backups restarts from RDB. Cons: more disk space used, slightly more complex to manage than single-method persistence. When both are enabled, AOF is used for data recovery as it contains the most up-to-date dataset. Data recovery process. When Redis starts up, it automatically checks for persistence files in its working directory. If both append-only AOF and dumprdb are present and AOF is enabled, AOF will be used for recovery as it guarantees the most complete dataset. If only dumprdb is present, it will be loaded. If only append-only AOF is present, it will be replayed. If neither is present, Redis starts with an empty dataset. Conclusion on persistence. Redis persistence mechanisms are robust and flexible. The choice depends on a careful analysis of your application's data loss tolerance, performance requirements, and recovery time objectives. For most critical production applications, enabling both RDB and AOF with append sync everysec offers a strong and reliable solution for ensuring your Redis data is durable and recoverable. In the next chapter, we will shift our focus from individual Redis instances to building highly available and scalable Redis deployments using replication, Sentinel, and cluster. High availability and scale. Replication, Sentinel, and cluster. We've explored Redis's various data structures, advanced features, and persistence options for durability. A single Redis instance, while fast and powerful, introduces several problems when deployed in a production environment. Single point of failure, SPOF. If the server hosting your Redis instance goes down, your application loses access to data and may stop functioning entirely. Scalability limits. A single Redis instance runs on a single CPU core, limiting its ability to handle extremely high read or write loads, or to store datasets larger than the available RAM on one machine. To address these challenges, Redis offers robust solutions for high availability, HA, and horizontal scalability. Replication, Sentinel, and Cluster 1. Replication. Redundancy and read scaling. Replication is the simplest form of high availability and primary scaling mechanism in Redis. It allows you to create exact copies of your Redis dataset on multiple instances. How it works. Master replica architecture. You designate one Redis instance as the master. All other instances are replicas. Asynchronous replication. The master handles all write operations. As soon as write commands are executed on the master, they are asynchronously replicated to all connected replicas. Read scaling. Replicas can handle read operations. By directing read traffic to multiple replicas, you can significantly scale the read capacity of your application and offload the master. Failover capability. If the master fails, a replica can be promoted to become the new master, though this requires manual intervention or an external system like Sentinel. Configuration, redis.conf or command line. On each replica instance, you configure it to replicate from a master. Replicaoff 192.168.1.16379 hash IP address and port of the master. Or for an older style, slaveoff 192.168.1.16379. The master requires no special configuration to enable replication, other than potentially setting requirepes. Advantages of replication: high availability, provides redundancy. If the master fails, a replica can take over. Read scalability, distribute read load across multiple replicas. Read-only replicas. Replicas can be used for things like running BGSAVE or long-running reports without impacting the master's performance. Disadvantages of replication: manual failover. Replication alone doesn't provide automatic failover. If the master goes down, a human or an external system is needed to promote a replica and reconfigure clients. Write scalability. Writes still go only to the master, so write throughput is limited by a single instance. Memory limit. The entire dataset must fit into the RAM of a single master instance. 2. Redis Sentinel. Automated failover and monitoring. Redis Sentinel is a distributed system that automates the high availability of Redis. It monitors your Redis instances, performs automatic failovers if a master goes down, and notifies clients about the new master. How it works: distributed Sentinels. You deploy multiple Sentinel processes, typically an odd number, like 3 or 5, for quorum. These Sentinels act as a cluster, communicating to agree on the state of Redis instances. Monitoring. Sentinels constantly monitor master and replica instances to check if they are reachable and functioning correctly. Automatic failover. If a master is detected as failed by a majority of Sentinels, a quorum, they initiate an automatic failover process. They elect a new master from the healthy replicas. They reconfigure the remaining replicas to replicate from the new master. They update the old master to become a replica of the new master once it recovers. Configuration provider. Clients are configured to connect to Sentinels, not directly to the master or replicas. Sentinels then tell the clients the current address of the master. If a failover occurs, Sentinels direct clients to the new master, providing application transparency. Configuration, sentinel.conf. Each Sentinel instance needs a configuration file. Port 26379, hash default Sentinel port. Dir TMP. Sentinel monitor MyMaster 192.168.1.16379, 2 hash MyMaster. Name, IP, port of master. Quorum, 2 means 2 Sentinels must agree for failover. Sentinel down after milliseconds MyMaster, 5000 hash master, considered down if unresponsive for 5 seconds. Sentinel failover timeout MyMaster, 60,000 hash max time for failover process. Sentinel can failover MyMaster yes hash, allows Sentinel to initiate failover for this master. Advantages of Sentinel. Automated high availability. Automatically detects master failures and performs failover without manual intervention. Centralized configuration. Sentinels provide a dynamic discovery mechanism for clients to find the current master. Monitoring and notification. Sentinels can be configured to send notifications, e.g., via scripting, about Redis events. Disadvantages of Sentinel. Complexity. Requires deploying and managing multiple Sentinel processes. Still single write point. Sentinel manages HA for a master replica setup, but writes still happen on a single master, so it doesn't scale write operations. Memory limit. The entire dataset must still fit in one master's RAM. 3 Redis cluster. Horizontal scalability and sharding. Redis cluster is Redis's solution for horizontal scaling. It allows you to automatically shard your dataset across multiple Redis instances, providing both high availability and scalability for writes and reads. How it works: sharding, partitioning. The dataset is automatically partitioned across multiple Redis master nodes. Each master in the cluster holds a subset of the total dataset. Hashing slot concept. The entire key space is divided into 16,384 hash slots. Each Redis master node is responsible for a subset of these hash slots. Redis determines which slot a key belongs to by hashing the key name. Automatic redirection. Clients can connect to any node in the cluster. If a client sends a command for a key that belongs to a different node, the current node will respond with a redirection (MOVED) error, telling the client to connect to the correct node. Smart clients automatically handle this redirection. High availability. Each master node can have its own replicas. If a master node fails, its replica is automatically promoted to become the new master for its hash slots, ensuring continuous operation. No central authority. Redis cluster uses a peer-to-peer approach. Each node stores the cluster configuration and communicates with other nodes to maintain a consistent view of the cluster state. This avoids a single point of failure in the control plane. Configuration simplified. You start multiple Redis instances in cluster mode and then use Redis CLI to create and manage the cluster. Example of a Redis.conf for a cluster node. Port 7000 hash unique port for each node. Cluster enabled yes. Cluster config file nodes -7000.conf hash automatically generated and managed. Cluster node timeout 5000. Append yes hash for persistence within each node. To create a 3 master, 3 replica cluster, 6 nodes total. Redis CLI cluster, Create 127.0.0.1:7,000.0.0.1:7001, 127.0.0.1:7,002, cluster replicas 1. This command sets up 3 masters and configures 3 replicas to follow them, 1 replica per master. Advantages of Redis cluster. Horizontal scalability. Scales writes and reads by distributing data across many nodes. Automatic sharding. Redis handles data partitioning and rebalancing. High availability. Automatic failover for individual master nodes. Seamless resharding. You can add or remove nodes dynamically without downtime, and Redis handles moving hash slots around. Disadvantages of Redis cluster. Complex setup and management. More complex to set up, monitor, and troubleshoot than standalone or Sentinel deployments. Key-level operations only. Transactions, multi-exec, and Lua scripts involving multiple keys are only possible if all keys involved hash to the same slot, and thus reside on the same node. Cross-slot operations are not atomic, not a replacement for all SQL needs, designed for key value and data structure operations, not complex relational queries. Client library support requires a clusterware client library, which often means an additional dependency. Choosing your scaling strategy. Feature standalone Redis replication, Sentinel Redis cluster. High availability, no manual failover, automatic failover, per shard. Write scalability, no single master, yes, across masters. Read scalability, no yes, across masters and replicas. Memory limit, single machine, distributed, sum of nodes. Setup complexity, low, medium, high. Cross-key operations, yes, all data on one node. Yes, all data on one node. Yes, all data on one node, limited, must be on same slot. Typical use case development. Simple caches, read-heavy apps. Backups, production HA for non-sharded DB large-scale, high-throughput apps. For many applications, a master replica setup, managed by Redis Sentinel strikes a good balance between simplicity, performance, and high availability. Redis cluster is reserved for those scenarios where the dataset or write throughput requirements exceed the capabilities of a single Redis instance. By selecting the appropriate architecture, be it simple replication, Sentinel-managed high availability, or a fully sharded cluster, you can ensure your Redis deployment meets the demands of modern, scalable applications. In the final practical chapter, we'll cover optimizing your applications, monitoring, and security best practices for Redis. Optimizing your applications, performance, monitoring, and security. You now possess a comprehensive understanding of Redis's capabilities, from its core data structures to advanced features and high-availability architectures. However, deploying Redis in production isn't just about functionality. It's about ensuring it runs efficiently, reliably, and securely. This chapter delves into the critical aspects of performance optimization, proactive monitoring, and essential security practices. Performance optimization, squeezing more out of Redis. Redis is inherently fast, but poor application design or suboptimal configuration can bottleneck its performance. 1. Network latency, minimizing round trips. Pipelining. As discussed in Chapter 8, pipelining is your best friend. Batching multiple commands into a single network request drastically reduces the impact of network latency. Always use pipelining when sending multiple commands sequentially from your application. Transactions, multi-exec. While ensuring atomicity, transactions also implicitly use pipelining, offering performance benefits for a series of operations. Lua Scripting. For complex, multi-step operations or custom commands, Lua scripts, Chapter 9, execute entirely on the server, eliminating multiple client-server round trips. 2. Efficient data access. Leveraging data structures. Choose the right data structure. This is paramount. Using a set for unique elements rather than a list, or a hash for structured objects instead of multiple strings, can lead to significant memory and CPU savings. Avoid keys in production. As repeatedly warned, keys is a blocking command that scans the entire key space. Use scan for production environments to iterate over keys incrementally. Optimize hash access. Use HMGET to retrieve multiple fields from a hash in one call, and HSET with multiple field value pairs to set many fields. Utilize range queries judiciously. While LRANGE and ZRANGBYSCORE are powerful, limit the size of data returned. Retrieving thousands of elements in a single query can put strain on both Redis and the client network. 3. Memory management. Keeping Redis lean. Set max memory. Always configure max memory in your redis.conf to prevent Redis from consuming all available RAM, which can lead to system instability. Choose an appropriate max memory policy. Noviction default prevents writes when memory limit is reached, causes errors. All keys LRU evicts least recently used keys from all keys. Volatile LRU evicts least recently used keys with an expiry set. All keys random, volatile random eviction policies. All keys LFU, volatile LFU, evicts least frequently used keys, requires Redis 4.0 plus and LFU log factor, LFU decay time settings. Choose a policy that evicts the least valuable data while preserving critical information. Use memory-efficient data structures. For small hashes, lists, and sorted sets, Redis can sometimes use highly optimized, memory-efficient internal representations, zip lists in sets. However, if these grow too large or contain certain types of data, they convert to regular hash tables skip lists, consuming more memory. Tune hash max zip list entries, list max zip list entries, etc. in redis.conf if necessary. Expire keys. Make heavy use of expire and SETEX for transient data, caches, sessions. This ensures old, unneeded data is automatically removed. 4. System tuning. Disable transparent huge pages, THP. On Linux, THP can lead to high latency spikes with Redis. It's strongly recommended to disable it. Swap control. Avoid swap usage. Redis performs best when it operates entirely within physical RAM. Monitor swap usage and ensure enough free RAM. Network configuration. Ensure network interfaces and driver settings are optimized for high throughput and low latency. Monitoring. Keeping a finger on the pulse. Proactive monitoring is essential to detect issues before they impact users and to understand Redis's behavior under load. 1. Built-in Redis commands. Info. Provides a wealth of metrics categorized by sections: server, clients, memory, persistence, stats, replication, CPU, cluster, keyspace. Info memory. Used memorious resident set size. Info stats. Total connections received, total commons processed, instantaneous ops per sec, rejected connections, expired keys, evicted keys. Info clients, connected clients, blocked clients. Info persistence, information about RDB and AOF. Monitor, streams every command processed by the server in real time. Useful for debugging specific issues, but high overhead. Don't use in production unless absolutely necessary for short periods. Client list. Lists all connected client connections, their ID, address, command in progress, etc. Latency provides detailed latency statistics for various Redis commands and operations. Latency Doctor gives a human-readable analysis. 2. External monitoring tools. Relying solely on Redis CLI is not scalable. Integrate Redis monitoring with your existing infrastructure monitoring solutions. Prometheus plus Grafana, popular open-source stack. Use the Redis exporter to scrape Redis metrics and visualize them in Grafana dashboards. Cloud provider monitoring. AWS CloudWatch for Elasticache, Azure Monitor for Azure Cache for Redis, Google Cloud Monitoring for Memoristore. APM tools. Many application performance monitoring, APM tools, e.g. Datadog, New Relic, offer Redis integrations to track health and performance alongside your application. 3 key metrics to monitor. Memory usage. Used memory. Watch for steady increases indicating memory leaks or inefficient usage. Latency. Instantaneous ops per sec, average command latency, from latency output or external tools. Spikes indicate bottlenecks. Connections, connected clients. Monitor for unusually high numbers indicating client connection leaks. Evictions, expirations, evicted keys, expired keys. High eviction rates indicate you're running out of memory or your max memory policy is too aggressive. Persistence. Monitor RD blasts of time, AOF AFLastrite status to ensure backups are working. Replication Sentinel cluster status. Ensure all nodes are healthy, masters are serving, replicas are in sync, and sentinels are in quorum. Security. Protecting your Redis instance. Redis, by default, is built for speed and ease of use, not necessarily for out-of-the-box strong security. It's crucial to harden your Redis deployments. One network security, where Redis lives. Firewall rules, the most critical step. Restrict access to Redis ports, 6379, 26379 for Sentinel, only to trusted IP addresses, e.g., your application servers, monitoring servers. Do not expose Redis directly to the public internet. Binding to specific IP addresses. In redis.conf, use bind 127.0.0.1 for localhost only or bind private tape address for specific internal network interfaces. Avoid bind 0.0.0. unless protected by strong firewall rules. Protected mode. Redis 3.2 Plus introduced protected mode yes, default. This prevents clients from connecting from outside the loopback interface if no bind address or require pass is set. Keep it enabled. Separate networks VPCs. Deploy Redis instances in private network segments or virtual private clouds, VPCs, that are isolated from public access. 2. Authentication. Who can connect? Require pass. Set a strong password in redis.conf. Require pass your strong password her. Never use Redis without authentication in production. ACLS access control lists in Redis 6 Plus. For more granular control, Redis 6.0 introduced. You can define specific users with limited permissions, e.g., read-only access, access to only certain commands or key patterns. Hash in redis.conf. User default off some random password hash disable default user with no password. User myapuseron plus at all flushall debug app. Asterisk another secure password hash custom user for app keys. No flushall debug. ACLS are a significant security enhancement for multi-tenant environments or complex applications. 3. Persistence and backup security. Restrict access to DB file name and append file name. Ensure these files and the directories they live in have appropriate Unix permissions to prevent unauthorized access. Encrypt backups. If transferring RDB AOF files for disaster recovery, ensure they are encrypted in transit and at rest. 4. Command renaming disabling. Rename dangerous commands. Commands like flushall, flushdb, keys, monitor, and debug can be dangerous in production. Rename them to obscure names or disable them in redis.conf. Rename command flushall, hash disable flushall. Rename command debug hidden. 5. Principle of least privilege. Grant only the necessary permissions to your application, user's credentials. If a microservice only needs to read a cache, give it read-only access. Avoid running Redis as root user. Use a dedicated, unprivileged user. Summary. Optimizing, monitoring, and securing your Redis deployments are not afterthoughts. They are integral to building high-performance, resilient, and safe applications. By implementing best practices for memory management, choosing efficient data operations, leveraging monitoring tools, and rigorously securing your instances, you can ensure Redis remains a fast, reliable, and trustworthy component of your infrastructure. In our final chapter, we'll offer some overarching best practices, discuss when Redis is the right tool and when it isn't, and provide a look at future trends and resources for continued learning. The road ahead. Best practices and future directions. Congratulations! You've journeyed through the intricate world of Redis, from its fundamental data structures to advanced features like streams and Lua scripting, and learned how to build resilient, high-performance, and secure applications using common architectural patterns. This final chapter aims to consolidate your understanding with overarching best practices, guide you on when to choose Redis and when to reconsider, and point you towards continuous learning in the ever-evolving landscape of data storage. Overarching best practices for effective Redis usage. Beyond the specific recommendations in each chapter, a few general principles apply to nearly all Redis deployments. Embrace test-driven development with Redis. The Redis CLI is your friend. Before writing application code, experiment with commands in the CLI until you fully understand their behavior, edge cases, and return values. This hands-on approach builds intuition and prevents common pitfalls. Design keys thoughtfully, keep keys short, reduces memory consumption and network bandwidth. Use a consistent naming convention. Organize your key space logically, e.g. user, id, profile, product, SKU, stock, session, sessionid. This improves readability and makes pattern-based operations easier. Avoid overly complex key schemes. Keep them understandable. Use expire aggressively. For any data that can be regenerated or becomes stale, set an expiration. This automatically frees up memory, reduces maintenance overhead, and prevents your Redis instance from becoming a memory hog with forgotten data. Prioritize pipelining. Always consider batching commands where possible. Network latency is often a bigger bottleneck than Redis's raw processing power. Your application's performance will thank you. Leverage Redis modules judiciously. Modules like Redis Search, Redis JSON, or Redis Graph offer incredible power, but they add complexity. Use them when their specialized functionality significantly simplifies your architecture or provides a performance gain that traditional approaches can't match. Don't adopt a module just because it's new and shiny. Monitor everything. Don't wait for production issues to realize Redis is struggling. Set up comprehensive monitoring for memory usage, latency, connection counts, persistence, and replication status. Early detection is key. Security first. Never run a production Redis instance unprotected. Always use strong passwords, require PES, bind to specific private IPs, and implement strict firewall rules. Consider ACLs for fine-grained control if using Redis 6+. Understand your data model. Before choosing a Redis data structure, think deeply about your access patterns. Do you need unique members? Set sorted set. Do you need order, list, sorted set? Do you need key-value pairs within a key? Hash. Do you need time series data or a durable log? Stream. Do you need only counts or the actual items? Hyperlog v's set. Scale appropriately. Don't start with a cluster if a single instance with persistence and a solid client-side implementation suffices. Scale up more RAM CPU, and then out replication, Sentinel, cluster as your needs evolve. Overengineering prematurely adds unnecessary complexity. 10. Regular backups. Even with AOF and RDB, ensure you have a robust backup strategy in place, ideally storing RDB files remotely and testing your recovery process periodically. When is Redis the right tool? Redis is an invaluable and versatile tool, but it's not a silver bullet. Its strengths make it shine in specific scenarios: high-speed data access. When you need microsecond latency reads and writes, caching, session stores, real-time analytics. Volatile or ephemeral data. Perfect for data that doesn't need long-term archival or can be easily regenerated, e.g. API rate limits, transient user sessions, short-lived queues. Structured yet flexible data. Its rich data structures fit many common application patterns perfectly without rigid schemas. Real-time interactions. For features requiring instant updates and push notifications, chat, live comment feeds, leaderboards. Offloading primary databases. Reducing load on slower, more expensive backend databases. Distributed coordination. For reliable locks, message queues, and shared counters across microservices. When to reconsider Redis and alternatives. While capable, Redis might not be the best fit for every scenario. Primary relational data. If you need complex joins, advanced querying capabilities, or strict transactional integrity across multiple operations on different keys, a traditional relational database, PostgreSQL, MySQL, is likely more appropriate. Large, unbounded datasets. While Redis scales, storing truly massive datasets, terabytes or petabytes, that don't fit into RAM even across a cluster, is better suited for disk-based databases or data warehouses, e.g. Cassandra, MongoDB, Snowflake. Complex full-text search, without Redis Search. While Redis Search extends Redis for scenarios demanding highly sophisticated search capabilities, dedicated search engines, Elasticsearch, Solr, might offer more out-of-the-box features. Long-term, highly structured document storage. While Redis JSON helps, For large, nested JSON documents with complex indexing needs, a dedicated document database, MongoDB, Couchbase, might be more optimized. Strictly audited, financial transaction logs. While AOF provides durability, an immutable append-only log designed for financial auditing might require specialized ledger databases. Heavy computation within the database. Redis is fantastic for data manipulation, but not designed for complex analytical queries that would typically run in a data warehouse or analytical database. Future directions and continuous learning. The Redis ecosystem is vibrant and constantly evolving. Here are a few areas to keep an eye on and resources for continued learning. Redis core evolution. New Redis versions bring performance improvements, new commands, and sometimes entirely new data structures, like streams in 5.0 and the upcoming Shard PubSub. Stay updated on the official Redis blog and release notes. Module development. The landscape of Redis modules is rapidly expanding. Look for innovative modules that address specific domain problems. Cloud-hosted Redis. Cloud providers are continually enhancing their managed Redis services. AWS Elasticache, Azure Cache, Google Memoristore, Redis Cloud. These offer simplified operational management, automatic scaling, and advanced features. Serverless and edge computing. The low-latency nature of Redis makes it a compelling choice for use in serverless functions and at the edge, closer to users. Client libraries. While the core protocol remains stable, client libraries are always improving, offering better performance, more idiomatic APIs, and support for the latest Redis features. Resources for continuous learning. Official Redis documentation. Redis.io is your primary source for accurate and up-to-date command references, tutorials, and deep dives into Redis internals. Redis University offers free online courses covering various aspects of Redis, from fundamentals to advanced topics. Redis community forums Stack Overflow, a treasure trove of solutions to common problems and discussions. Blogs and articles. Many developers and companies share their experiences and solutions using Redis. Follow prominent engineering blogs. Conferences. Attend Redis Conf or other database cloud conferences to learn about the latest developments and best practices. Mastering Redis is an ongoing journey. The concepts and patterns you've learned in this book provide a strong foundation. By continuing to experiment, read, and apply Redis to your own projects, you'll uncover new ways to leverage this powerful tool and stay ahead in the dynamic world of modern application development. Go forth and build fast, reliable, and scalable applications with Redis.